Thousands of planes, just sitting in the desert. They'll never fly again. But each one? Millions of dollars being carefully stripped away, bolt by bolt, right now. One engine, 30 million. Business class seats, a few thousand each. Even the coffee maker from an old Boeing gets auctioned off. People think aircraft boneyards are graveyards. But the truth is, they're incredible recycling operations on the planet. Today, we're going where almost no one gets to go. To watch a 150-ton giant get torn down to scrap metal in 30 minutes. And why this isn't the end at all. It's a whole new beginning. Why the desert? That's the first question that pops up when you see these thousands of acres packed with plains. It's pushing 100 degrees Fahrenheit out here, and the humidity's basically zero. Perfect conditions to keep metal from rotting and rusting. Planes can sit here for decades and still look like they rolled off the tarmac at JFK yesterday. But not all of them are here to die. A lot are just waiting for better times. The airplane recycling process starts with what the pros call harvesting. This is the most profitable part of the job. When an airline decides a plane is no longer flight-worthy, engines are the first things to go. One of those engines can run anywhere from $10 to $30 million in working condition. They're pulled using special lifts and shipped off for diagnostics. Even if the airframe itself is old, those engines can keep flying on other aircraft for years to come. It's like a heart that keeps beating in another body. Besides the engines, they remove the auxiliary power unit. That's a small engine in the tail of the plane that provides electricity when the main motors are shut down. That thing's worth serious money too. Next, we step inside the cockpit. For aviation fans, this is like Aladdin's cave. There are hundreds of switches, screens, and computers. Each black box or navigation instrument can fetch several thousand or even tens of thousands of dollars on the secondary market. Workers remove all the equipment very carefully, pack it into special anti-static boxes, and send it for testing. Same goes for the passenger cabin. You'd be surprised, but even the seats have value. A set of business class seats can be sold for several $1,000s to private companies or movie studios building sets. Galleys, meal carts, even coffee makers, everything goes up for sale. There's nothing worthless on a plane until it's just an empty metal tube. Once everything valuable is stripped out, the environmental specialists step in. An aircraft is a complex machine packed with hazardous fluids. Every last drop has to be drained. The fuel tanks of a large plane can still hold several hundred gallons of kerosene that can't be pumped out during normal operations. Hydraulic fluid also needs draining. It's highly toxic, along with lubricant from all the mechanisms and antifreeze. Just imagine, the total volume of all these technical fluids can reach 500 gallons. All of it gets drained into special tanks for proper disposal. Workers also remove batteries, fire extinguishers, and oxygen cylinders. If even one of those cylinders stays inside when the heavy machinery moves in, it can explode with the force of an artillery shell. When the plane becomes completely clean, the most spectacular part begins, destroying the fuselage. Here we see a giant excavator at work, but instead of a bucket, it's equipped with hydraulic shears. They're sometimes called the guillotine. The operator of this machine is a true master. He drives up to the aircraft and starts chomping off pieces of the wings. The sound is like someone tearing open a giant soda can, only 1,000,000 times louder. The metal crunches, cracks, and gives way under pressure of several thousand pounds per square inch. First they cut off the wings, then the tail section. All of this is done according to a specific plan, so the structure doesn't collapse onto the machine itself. Next, the excavator tackles the fuselage. It simply slices this massive steel tube into chunks about 20 feet long. This is done so these pieces can be loaded onto regular trucks and hauled to the metal mill. Watching what was once a majestic airliner that flew at 30,000 feet get turned into a heap of mangled metal in 30 minutes. It's a sight that makes you think about how fleeting time really is. But the equipment operators don't have time for philosophy. They need to sort the scrap as fast as possible. Sorting is the key to profit in this business. An aircraft is made up of different metals, and they can't be mixed. About 80% of the weight is aluminum, but it also comes in different grades. The skin is one alloy. The structural beams inside are another. There's also titanium, which is used in high temperature areas, like near the engines. Titanium costs several times more than aluminum, so there's a real hunt for every piece of this metal. There's also steel in the landing gear, and some copper in those leftover wires that couldn't be pulled out by hand. Workers use magnets and special scanners to separate these piles of metal. A lot of people think aircraft scrap is the end of the story, but it's actually the beginning. The aluminum from these planes, it's the highest quality metal. They melt it down at around 1200 degrees Fahrenheit and make new ingots. From that aluminum, they can then make just about anything. Beer cans, parts for new cars, or even new aircraft. It's a closed loop where nothing goes to waste. Experts say roughly 95% of a modern passenger jet's weight can be recycled and used again. That's an incredible number for such complex machinery. Here's a fun fact for those who love numbers. In 1 year at a boneyard like this, they can completely dismantle up to 200 aircraft. If you take the average weight of each at 150,000 pounds, that's 30 million pounds of metal going back into the economy. This is $1 billion business, and it's only growing because airlines are trying to upgrade their fleets faster to more fuel-efficient models. Older planes become too expensive to maintain, so they end up right here, under the Arizona sun. There's always something a little sad about watching planes die, but at the same time, I'm blown away by how incredibly organized this whole process is. There's no chaos here. Every swing of the excavator, every step a worker takes with a wrench in hand, it's all calculated down to the second. This is a massive machine that converts the past into the future. We've just watched hydraulic power transform a symbol of technological progress into raw material for new achievements. And even though these aircraft will never take to the skies again, they live on in the things we use every day. As we walk across this yard, there's a constant crunch of broken glass and insulation debris under our feet. The air smells like hot metal and dry grass. It's a unique atmosphere that's tough to capture in words. This is where engineering genius meets inevitable destruction. But it's not destruction for destruction's sake. It's destruction for the sake of creating something new. And that's really what our civilization is all about. We're constantly recycling the old to build something better, faster, and more efficient. I hope you enjoyed peeking behind the fence of this aircraft graveyard with me. Now, next time you're flying off on vacation, you'll know what awaits your plane in 20 or 30 years. And it's not scary at all. It's just another chapter in the life of metal and technology. Thanks for watching my explorations. Hit that like button if you're into massive machinery like this, and subscribe so you don't miss new journeys to the most fascinating places on our planet. We'll find plenty more spots where metal tells us its incredible stories. See you in the next video, where we'll tear apart something just as epic. Bye. Today, I dragged you out to a place where dust isn't a sign of bad housekeeping. It's the smell of serious money and the foundation of everything we call civilization. We're at a cement plant. Look at this landscape. It's like we just landed on Mars, except instead of red sand, everything here is coated in a fine layer of gray powder. Just think about it. We produce over 4 billion tons of this stuff every year. If you tried to stack it all up, you'd get a mountain that would dwarf any skyscraper in New York. We start our journey at the very beginning, the quarry. Just look at these machines. These giant dump trucks look like they escaped from a Transformers movie, but instead of saving the world, they just haul limestone all day long. One wheel on this thing stands about 12 feet tall. That's twice the height of your average pedestrian, who's probably sipping a latte somewhere downtown right now, completely unaware that their apartment is held up by the efforts of these steel monsters. Limestone is the foundation of everything. It's ancient shells and skeletons of sea creatures that decided to die right here millions of years ago, so we could build another shopping mall today. When limestone gets blasted in the quarry, chunks of rock can be the size of a compact car. But for the plant, that's way too coarse. That's where the primary crusher comes in. It's this massive steel jaw that chews through rock as easily as you crunch chips in front of the TV. The noise here is so intense that your noise-canceling headphones would just give up and retire. After the crusher, we get chunks no bigger than 3 or 4 inches. Next, all this mass goes onto a conveyor belt that stretches for miles. It looks like an endless snake crawling through fields and roads, straight to the heart of the plant. Now we enter the raw materials prep shop. This is where the cooks of the industrial world mix their secret recipe. Besides limestone, we need clay, sand, and a bit of iron ore. All of this has to be ground into a fine powder called the raw mix. You can't even imagine how precise this ratio has to be. The lab checks the composition every 15 minutes. If they're off by even 1%, your entire skyscraper might just decide it'd rather lie down than stand up. Chemistry rules everything here. It's pure science, where we make molecules dance to our tune. And now brace yourselves, because we're approaching the hottest spot on the map. This is the rotary kiln. If you ever thought summer in Texas was hot, you knew absolutely nothing about life. This kiln is a gigantic steel tube over 600 feet long. It's tilted at a slight angle and constantly rotating. Inside, it's straight up hell. Temperatures in there climb to 2,700 degrees Fahrenheit. That's so hot that iron starts to weep. At this moment, what we call decarbonization happens. The limestone breaks down, releasing carbon dioxide, and transforms into calcium oxide. This is the moment of truth. The raw material begins to melt and clump into little gray balls called clinker. Clinker is basically a semi-finished product, cement in its embryonic state. Just think about the energy needed to keep a fire like that going. They burn everything here, from coal to old car tires. So, here's something wild. Old tires make excellent fuel because they burn completely at these temperatures, leaving behind nothing but energy for our kiln. It's like nature's own brutal recycling program. When this red-hot clinker exits the kiln, it looks like tiny meteorites that just fell from the sky. It needs to be cooled immediately. Massive fans blast it, dropping the temperature from thousands of degrees down to 160 degrees Fahrenheit in just minutes. The whole thing looks incredibly dramatic. Clouds of steam, glowing metal, and that distinctive crackling sound. But this still isn't cement. The final stage is the last grinding. We take our clinker, add a bit of gypsum to it, about 5% of the total weight, and send it into a ball mill. This is another horizontal tube, but inside it's packed with thousands of steel balls. As the tube rotates, these balls drop and pulverize the clinker into such a fine dust that it becomes softer than the flour your grandma uses to bake pies. The gypsum here is needed, so the cement doesn't set instantly when you add water to it. Without gypsum, construction workers simply wouldn't have time to carry a bucket of mix to the wall. This grinding process is incredibly loud and consumes enough electricity to power a small town. But the result is worth it. Now we have a gray powder that can turn into stone on command. We store it in massive silos, these concrete towers that can reach up to 150 feet tall. Each silo holds thousands of tons of finished product. Look at these trucks lined up in queue. They haul this powder all across the country. Rail cars, barges, bags at hardware stores. Cement is everywhere. Every American indirectly consumes close to 1,000 pounds of cement each year. We literally live inside this material. Our roads, bridges, building foundations, even power plant dams. All of it depends on those gray granules we just saw inside that blazing kiln. People often tell me this is a dirty business. And yeah, it's true. There's no cement without dust and fire. But that's where its raw beauty lies. This is an industry that doesn't tolerate weakness. Everything here is massive, everything scorching hot, and everything operates at the physical limits of what materials can handle. It's a real battle between man and matter, where we force solid rock to go liquid, then solid again. But this time in exactly the shape we need. Next time you're walking down a sidewalk or staring up at bridge supports, remember the long journey that stone took. From an explosion in a quarry to 2,700 degrees inside a kiln to steel balls in a grinding mill. It's a long road, packed with chemical transformations and incredible engineering genius. We've learned to control processes that took nature millions of years to create, and we're doing it at a scale of billions of tons. I hope you enjoyed this journey through the world of dust and fire. Personally, I always love seeing how something that looks so simple on the surface turns out to be incredibly complex inside. It reminds us that behind every ordinary thing, there's an entire army of people, machines, and scientific calculations. All right, I'm off to clean the dust off my camera, and you, don't forget to look at the world around you a little more carefully. See you at the next factory, where we'll definitely find something huge, loud, and absolutely fascinating. It's interesting that even in our age of digital technology and artificial intelligence, we're still dependent on a red-hot tube filled with limestone. You can write code for a new app, but you can't live in it. You'll still need a foundation, walls, and a roof. And that's exactly why cement plants aren't going anywhere. They're a reality you can't ignore. It's physics you can't hack. And that's what I love most about it. Here, everything is real. Touch this furnace, you'll get burned. Stand under that clinker stream, you'll get buried. No filters, no fakeness, just pure industrial power. We've traveled a lot of miles today, seen tons of raw materials and giant machinery, and every single time, I can't stop marveling at the scale. Humanity. This weird creature that decided caves weren't enough and started turning mountains into powder to build its own mountains out of glass and concrete. It's ambitious, it's bold, and it's very human. And you know what else is human? Subscribing to my channel right now. Alright, that's it. Tour's over for today. The air here's getting too thick, and my lungs are already begging for some clean forest air. But I'm sure tomorrow I'll want to come back to where the big machines work, because that's where you feel the real rhythm of our world. See you. Today, we're not at some sleek, modern factory. We're heading back in time, to an era when the entire world was engulfed in flames, and one nation that had peacefully built cars and refrigerators did something absolutely mind-blowing. This is the story of the arsenal of democracy, how American industry churned out so much weaponry in just a few years, it could have armed several planets. And we're looking at its crown jewel, the legendary flying fortress, the B-17 bomber. I spent weeks digging through archival blueprints, photographs, and records to tell you how a country that was making sedans for housewives yesterday started rolling out one bomber every single hour. So it's December 1941. Pearl Harbor's in flames, and America enters World War II. And the first question facing the government, where do we get planes? The B-17 bomber, developed by Boeing. It's an engineering marvel, but they're building barely any, almost one at a time. And the country doesn't need dozens, it needs tens of thousands of these machines. So President Roosevelt throws down the gauntlet to American industry, and that industry answers. And how it answers. Enter automotive giants like Ford and aircraft companies Douglas and Lockheed. They're told, guys, forget about cars. From now on, you build bombers. And that's when the real madness begins. Picture this. Ford, a company that had never built planes before, constructs from scratch in the middle of a Michigan cornfield, the world's largest factory at the time. Willow Run. This isn't just a factory, it's an entire city under one roof, a mile long. Over 40,000 people work here, many of them women coming into manufacturing for the first time. And they face a task that seems impossible. Put the production of a giant, complex bomber on an automotive assembly line. Nobody had ever done this before. You get why it was women, right? When America entered the war, millions of men, factory workers, farmers, mechanics, put on military uniforms and shipped out to the front. And suddenly, the factories that needed to produce tanks, ships, and planes sat empty. The country faced a massive labor shortage. So the government and industry turned to people they'd barely considered for heavy manufacturing before: women. A powerful propaganda campaign rolled out. Famous posters showing a strong woman in a work bandana, flexing her bicep with the words, "We can do it," appeared across the country. And women answered the call. Millions of housewives, waitresses, secretaries, and recent high school graduates went to work in the factories. For them, this wasn't just a paycheck. It was patriotic duty, a way to do their part for victory, while their husbands, brothers, and sons fought thousands of miles from home. They proved they could do men's work just as well, sometimes better, becoming the unstoppable force that allowed American industry to work miracles. And here's where the American government and industry made some incredibly powerful moves. First, the government essentially forced Alcoa to share its technology and funded the construction of dozens of new, massive aluminum plants across the country. Entire cities were built, for example, in the industrial states of Washington and Tennessee. Why there? Because aluminum production is an insanely energy-intensive process. It relies on electrolysis from alumina, and that requires cheap electricity. And in these exact regions, the government had just finished building giant hydroelectric dams on the Columbia and Tennessee rivers. It was a perfect match. Huge amounts of clean, cheap energy waiting for someone to use it. Second, raw materials. The main raw material for aluminum is bauxite. Most of it had been imported from South America before the war. When the war started, German submarines began hunting merchant ships, and that route became dangerous. So America dramatically ramped up mining of its own bauxite, mainly in Arkansas, and secured the sea routes from the Caribbean as much as possible. But the most amazing part of this story is the grassroots movement. The government launched a massive patriotic campaign with the rallying cry, "Turn in aluminum for victory." School children, housewives, Boy Scouts, the entire nation started collecting aluminum scrap. People turned in old pots, pans, milk cans, parts from household appliances. It didn't have decisive economic significance, but it had a colossal psychological effect. Every American felt that their old pot could become part of a flying fortress wing that would fly off to strike the enemy. As a result of these titanic efforts, in just a few years, from 1940 to 1943, aluminum production in the US increased sixfold. The country didn't just cover its own needs, it started supplying this strategic metal to its allies. And that's how, through the combination of government will, industrial might, and the patriotism of ordinary people, America transformed a scarce pot metal into an endless stream of winged metal that became the lifeblood of its bomber armada. After stamping, each part needed 2 holes drilled on each side for rivets. And that's when the women stepped onto the stage. The legendary Rosie the Riveters. Thousands of young women who just yesterday were housewives or waitresses now stood at workstations, drilling these holes with incredible speed and precision. And then the real concert began. Thousands of pneumatic riveting hammers pounding aluminum simultaneously, creating a deafening non-stop roar. This was the sound of the arsenal of democracy being forged. Women worked in pairs. One held a massive bucking bar from the inside, while the other hammered the rivet from outside. Each rivet had to be perfect, because the aircraft's strength depended on it. And this is where Ford unveiled its main automotive trick: modular assembly. They didn't try to build the entire airplane in one place. Instead, they broke it down into large sections, or modules. In one shop, thousands of people assembled just the nose section of the fuselage. In another, just the center section with the bomb bay. In a third, gigantic wings, each over 50 feet long. Each section was assembled on its own mini assembly line, where it was packed with everything necessary. Miles of wiring were run, hydraulic lines installed, equipment mounts fitted. This allowed dozens of teams to work in parallel, without getting in each other's way. And then, these ready-made sections, packed with internal modules, looking like giant chunks of an aluminum construction set, got wheeled over to the main assembly line. This was the climax, a line a mile long. At the start, there's just the center wing section. Then 2 fuselage halves get joined to it. The whole structure moves freely forward. At the next station, they attach the nose and tail sections. Further down, they mount the massive wings. And so, step by step, right before your eyes, from separate pieces, a gigantic, nearly 100-foot aircraft takes shape. At the final stations, they install 4 powerful Wright Cyclone engines, each churning out 1,200 horsepower, mount the landing gear, glaze the cockpit, and of course, fit its main argument. 13 heavy-caliber Browning M2 machine guns, which gave it the name Flying Fortress. At peak production, in 1944, the Willow Run plant rolled out 1 B-17 bomber every 63 minutes. Just think about that. Every hour, 24 hours a day, a brand new, battle-ready heavy bomber rolled through those factory gates. It was a non-stop river of steel, aluminum, and firepower. In total, during the war years, 3 companies, Boeing, Douglas, and Ford, built over 12,700 flying fortresses. This wasn't just a victory of technology, this was a victory of logistics, organization, and most importantly, people. 1.5 million ordinary Americans who put aside their peacetime lives and became soldiers on the industrial front. They proved that a free nation, when united by a common paycheck, is capable of genuine miracles. That was the arsenal of democracy in action. Thanks for watching. Hit that like button, subscribe, and see you next time. Without this unassuming rock, often mistaken for ordinary dark pebbles or heavy chunks of granite, modern electronics would instantly collapse into a pile of useless plastic and silicon. Tin ore, or more precisely its primary mineral, cassiterite, is the hidden foundation holding up our entire digital world. When we talk about high-tech, we name-drop gold or complex semiconductors, but this is the invisible glue binding billions of microscopic components into a single working system. Tin's journey begins deep in the planet's crust, where for millions of years, metal-rich solutions seeped into fractures in the earth, forming deposits that today drive the pace of human progress. Cassiterite, often called tinstone, has an incredible density and a distinctive diamond-like luster when fractured, though on the outside, it can look like ordinary brown or black rock. Mining this ore demands massive effort and specialized knowledge. The world's major reserves are concentrated in what's called the Tin Belt, stretching through Southeast Asia, China, Latin America, and Africa. The scale of extraction is staggering in its variety, from colossal open-pit mines and underground shafts to dredging operations on the ocean shelf. For example, off the coast of Indonesia, giant floating dredge factories pull up thousands of tons of tin-bearing sand from the seafloor, sifting it through complex filter systems to separate out the heavy ore particles. The process of transforming rock into pure metal is long and exhausting. Since tin content in ore is now low, the rock first undergoes multi-stage enrichment. It's crushed, washed, and separated using gravity methods that exploit cassiterite's high specific gravity. After obtaining the concentrate, the smelting stage begins in a furnace at around 2,200 degrees Fahrenheit. Here, under the influence of reducing agents, tin separates from oxygen and other impurities, transforming into a liquid silvery metal. But for the electronics industry's needs, this purity isn't enough. The metal goes through a series of refining processes to eliminate the tiniest traces of iron, copper, arsenic, or antimony. Only after this does it become the material we see in the form of solder. Solder. That's the main use for tin in the modern world. It's not just some auxiliary material. It's a critically important component of any electronic device. Previously, soldering used an alloy of tin with lead, but due to environmental requirements and health safety concerns, the world switched to lead-free technologies. Today, the latest circuit boards are joined using alloys where tin makes up 95 or even 99%. Every smartphone, laptop, control unit in cars, or satellite onboard computer contains several thousand soldered connections. Without tin's ability to wet the surfaces of other metals and create reliable electrical contact at low temperatures, mass production of electronics would be impossible. Factories that produce modern electronics operate with incredible precision, and that's where a key tool comes into play. In surface mount assembly shops, specialized machines deposit solder paste through stencils onto circuit boards with accuracy down to the micron. Then the board passes through reflow ovens, where the paste transforms into solid metallic connections. It's an automated process where every second and every milligram of metal matters. If the tin contains even minor foreign impurities, it can lead to microcracks or tin whiskers, thin thread-like crystals that grow from the solder and can cause short circuits. That's exactly why quality requirements for tin ore and purification methods keep getting stricter. The impact of tin on urban development and global energy is hard to overstate. Sure, we don't build house frames from this stuff, but it's in every lighting control system, every elevator, every safety sensor. The growth of smart cities relies entirely on billions of sensors and controllers, each one held together by tin solder. This makes it a critical strategic resource, with entire regions shaping their economic policy around the battle for control over its deposits. Countries with major cassiterite reserves become key players in the high-tech supply chain. But tin ore extraction comes with serious challenges. Deep open pits and seabed dredging reshape ecosystems, demanding strict reclamation standards. Responsible companies try to minimize environmental impact by restoring forests and cleaning water used in the refinement process. At the same time, recycling is playing a bigger role. Tin is a metal that can be cycled back infinitely. Recycling old circuit boards keeps the metal's high purity with way less energy than mining it from ore. This creates a closed-loop economy, where yesterday's shattered screen becomes the source material for a new device. Interesting fact, tin's been used for millennia. When it combined with copper to create bronze, it gave an entire era of human history its name. Back then, tin was hunted down as aggressively as we hunt for oil or gas today. But while ancient people made swords and cookware with it, today it's become a tool for transmitting information. That's the evolution of this metal's role. From the brute force of bronze weapons to the refined precision of a silicon chip, where tin provides the pathway for electrons to flow. The stone once prized for its ability to make copper hard is now valued for its malleability and conductivity in the micro-world. Technological progress demands ever-increasing quantities of this metal. The growth of renewable energy, solar panels, and electric vehicles creates additional demand. Each photovoltaic panel requires tin connections to harvest the sun's energy. Electric vehicles contain significantly more electronic components than internal combustion engine cars, making this element essential in the fight for climate neutrality. Thus, ancient cassiterite becomes fuel for the green revolution. It's crucial to understand that tin deposits are distributed extremely unevenly across the planet. This creates certain risks for global production stability. Any disruptions in ore supply from major mining regions instantly impact consumer technology worldwide. This pushes scientists to search for new methods of enriching even low-grade ores, as well as developing technology for extraction from deeper horizons. Every foot of new mine shaft, or every mile of surveyed deposit, is a guarantee that factories keep producing new devices, and the planet's digital network continues to expand. The transformation of tin from mountain rock to solder on a circuit board is an example of how humanity has learned to harness the special properties of materials to achieve remarkable results. It's about tin's ability to be the connecting link. When we look at a chunk of tin ore, we see not just a mineral, but the potential for millions of conversations, terabytes of transmitted data, and the operation of complex mechanisms that ensure our comfort. Tin remains a humble yet irreplaceable hero of the industrial stage, working where no one sees it, at the very heart of machines. Production chains that begin in quarries and end in the clean rooms of high-tech factories are testament to our global interdependence. Tin isn't just a detail on a circuit board, it's the backbone of economies across continents. The continuous flow of ore, concentrate, and finished metal is the circulatory system of industry. Every ton of cassiterite pulled from the earth passes through the hands of thousands of specialists before becoming part of our global information infrastructure. And as we move toward even greater automation and digitization, the role of this stone will only grow, proving that great achievements often start with very small but critically important details. So, tin ore is the real key to modernity. It teaches us to value resources that seem invisible, but without them, the world we know would cease to exist. This is a story about how nature gives us materials, and human ingenuity finds the perfect use for them, transforming heavy ore into the lightness of wireless communication and the speed of data processing. Every grain of cassiterite carries its contribution to global development, remaining an eternal reminder that high technology has its roots in the work of the earth, a stone-born origin. From dark depths to gleaming device cases, the journey of tin is the journey of progress itself. Imagine construction that's not just strong, but super lightweight, durable, and eco-friendly all at once. That's exactly the revolution that fiberglass rebar represents, a modern material that's gradually replacing traditional steel reinforcement in countries around the world. China is especially aggressive in producing it, a giant controlling a massive chunk of the global market. But what is this secret material that's changing the game? And why does geopolitics play just as big a role here as technology? Let's dig in. Fiberglass rebar consists of reinforcing rods made from a composite material based on fiberglass soaked in special resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and holds up under harsh conditions. Think acid rain, salt spray, and high humidity. To put it in perspective, standard steel rebar weighs close to 1 pound per foot of length, while fiberglass rebar weighs about a quarter pound for the same size. This means it's easier to work with, requires less spending on transportation and installation, which makes construction faster and cheaper. China plays a leading role in global fiberglass rebar production. Factories, located mainly in the eastern and central regions of the country, are equipped with modern pressing, forming, and fiberglass polymerization lines. Chinese companies produce over 500 million pounds of these materials annually, with exports accounting for roughly 60% of total global volume. China's huge advantage lies not only in scale of production, but in price. Thanks to low electricity and resource costs, Chinese products are often cheaper than competitors from the USA and Europe. But this is already triggering intense geopolitical discussions. If you look at the bigger picture, fiberglass rebar has become a real hot potato in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. This secret aspect is this: China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in countries across Asia, Africa, and Latin America, Beijing actively promotes this material through its global construction corporations working within the Belt and Road Initiative. This allows China to not only increase its presence in the global construction market, but also strengthen economic influence in regions through control over construction resources. The trend of using fiberglass rebar isn't just about savings or new materials. It's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the USA, where the number of bridges, roads, and buildings constructed using lightweight composites is growing. Unlike metal, this material doesn't corrode, so infrastructure becomes more reliable and durable. According to reports from the American Association of Building Materials, on average, the cost of construction using fiberglass rebar drops by 20%, and the service life of structures doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, reduced environmental impact, and industry growth. If you're building a bridge or a high-rise, instead of heavy steel rebar, you use thin fiberglass rods. They can be longer, lighter, and simpler to install. Plus, you don't have to worry that after years, they'll start rusting and causing concrete deterioration. China is already actively using its fiberglass rebar on huge construction sites. In the capital districts of Beijing, Shanghai, and Guangzhou, they're installing new highways and bridge crossings using these materials. Around the world, Chinese companies supply this rebar for projects in the USA, Europe, and Middle Eastern countries, strengthening their technological and economic presence. Everything starts with glass, the raw material for making fiberglass. Glass is made from a mixture of sand, limestone, and soda. These ingredients are sent to large furnace ovens, heated to temperatures of 2,700 degrees Fahrenheit. Here, the mixture melts, forming liquid glass. Then the molten glass passes through special openings called spinnerets, forming thousands of thin threads. These fibers are cooled and collected into bundles. This creates primary fiberglass, thin, flexible, and strong threads. To give the fibers necessary properties, they're treated with a special chemical solution, an organic binder or silane. This coating ensures strong adhesion between the fiberglass and the polymer matrix that will follow. The treated threads are collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main stage, forming the composite matrix. The raw material for this is polymer resins, usually epoxy, polyester, or vinyl, which have high strength characteristics and provide a resistance to moisture and chemical effects. The fiberglass bundles are dipped or soaked in the polymer resin solution. The fibers are evenly coated with polymer, and excess is removed so there are no lumps and irregularities. The prepared wet bundles are fed into a special forming line, an extruder. Here the molten composition is pushed through forming openings, giving it the shape of a rod or bar of the required diameter. Then comes an important operation, drawing and polymerization. The finished reinforcing rods are immediately sent for cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a single structure. Size and shape control is very important, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard fiberglass rebar diameter can range from 1/4 inch to 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During production, an action occurs through forming rollers that creates ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It holds firmly in the concrete mass and doesn't slip under loads. At the end of the production line, workers or automation cut the reinforcing rods to standard lengths, usually 20 feet or 40 feet. The rods are packed in bundles that are convenient to transport and store. Each batch of products undergoes testing for strength, flexibility, and corrosion resistance. Manufacturers often provide warranties for rebar service life of over 50 years, which is several times longer than the service life of ordinary metal reinforcement. Fiberglass rebar is gaining increasing importance in modern construction thanks to its lightness, strength, and corrosion resistance. Next, you'll see some of the most interesting projects where this innovative material is actively used. Delhi Metro Phase in India, a large-scale metro project where this rebar is actively used to reinforce tunnels and structures. This helps extend the service life of structures and reduce the weight of building materials. Jizan Flood Mitigation Channel, Saudi Arabia, the world's largest project using fiberglass rebar, involving reinforcement of long channels for flood control. Over 11 million meters of fiberglass rebar were used here, designed to ensure high resistance to harsh environments. Muskrat Falls Hydroelectric Project, Canada. Rebar manufacturers supply material for reinforcement that guarantees a long service life for the hydroelectric station, especially in conditions of contact with water and high humidity. Sunshine Skyway Rest Area. Seawall, USA, Florida. Marine structures where fiberglass rebar is the ideal material due to corrosion resistance in salt water. Here it reduces the need for repairs and extends the service life of the walls. Alligator River Bridge, USA, North Carolina. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Canadian Tunnels. Toronto TTC North Subway Extension. A project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic movements. This thing takes up 2,000 square feet and weighs 800 tons. It's called a megapress, or Gigapress, and over the last 3 years, it's changed how electric trucks are made just as radically as Ford's assembly line changed the auto industry 100 years ago. There are fewer than 30 of these machines in the world. A few of them are right here. And here's the kicker. Without them, a modern electric truck simply can't cost little enough for anyone to buy it. Intrigued? Then hit that thumbs up and let's go. Ready? I'll start with the problem, because without it, I don't understand why you'd even build such a monster. The body of a regular truck, or SUV, that's 200 to 400 separate stamped steel parts, welded together on a complex assembly line. Each part, its own die, its own station, its own welding robot, its own quality control. It's slow, expensive, and hard. And for an electric vehicle, it's critical for another reason. The battery weighs anywhere from 1,000 to 1,800 pounds, and if the chassis underneath is assembled from hundreds of metal pieces joined with weld seams, in a serious impact, the whole thing can come apart in ways the crash test never predicted. That's exactly why engineers came up with the idea of casting the entire rear or front section of the body, complete with all the brackets, reinforcements, and mounting points, in one single piece. One casting instead of 40 separate chunks. That's what the megapress does. The material, an aluminum alloy. Not the kind that goes into beer cans, but a specially engineered composition based on aluminum with additions of silicon, magnesium, and several other elements in precise proportions. The main requirement for it? It has to stay plastic during impact and not shatter into pieces. Sounds obvious, right? But with aluminum, this is actually incredibly difficult to achieve at these wall thicknesses. From about 1/10 of an inch to just over 1/6 of an inch in different zones of the casting. Developing this alloy for a specific press and specific part geometry took some manufacturers anywhere from 2 to 4 years. One factory spent over $150 million on materials, science research, and testing alone, before the first production parts even came off the press. This press develops forces from 6,000 to 9,000 tons. 6,000 tons. That's roughly the weight of 12,000 mid-size cars compressed into a single point. The two halves of the die slam together, and in that instant, there can't be even a microscopic gap in critical zones. Otherwise, molten aluminum bursts through as what's called flash, and the part gets scrapped. A die for a large structural casting weighs between 100 and 140 tons and costs $50 to $80 million. One die. And it's already baked into the price before the first car rolls off the line. They load aluminum into a melting furnace right next to the press and heat it to 1,400 degrees Fahrenheit, the temperature where metal becomes liquid and flows like water. But you can't just pour it into the mold. At that temperature, it oxidizes in seconds, and pores and inclusions appear in the part's body, drastically reducing strength. So the metal flows through a system of vacuum channels. At the moment of the shot, air is evacuated from the mold surface to a pressure below 4 millibars. That's about 250 times less than atmospheric pressure. The aluminum rushes into this vacuum at speeds from 20 to 35 feet per second and fills the entire mold cavity in 80 to 120 milliseconds. A human blinks in about 150 milliseconds. That means a part the size of half a truck is cast faster than you can blink. Right after filling, the press plunger compresses the metal with up to 9,000 tons of force. This is called intensification, which eliminates residual porosity and densifies the structure in critical zones. The whole thing, from mold close to mold open, takes between 120 and 180 seconds. 3 minutes, and you've got a complete rear body section for an electric truck that used to require 240 parts and 80 welding operations. But here's where the real risk begins. At that fill speed and that pressure, the die wears out. In the highest stress zones, where the metal flow is hottest and where the intensification pressure peaks, the tool steel starts to crack microscopically after just a few thousand cycles. It's called thermal fatigue, the same thing that happens to metal that's heated and cooled over and over. After roughly 5,000 to 8,000 cycles, the die gets pulled, sent out for repair and replacement of inserts in critical zones. That takes 3 to 5 days and costs anywhere from $300,000 to millions of dollars per repair. Servicing a single die over its full service life, 100 to 200,000 cycles, can cost more than the die itself. And all of that is baked into the cost of every single part. After pressing, the casting goes to X-ray inspection and CT scanning. The scanner penetrates the metal and builds a three-dimensional model of the internal structure. The algorithm compares it to a reference model and automatically flags zones with porosity, inclusions, or incomplete filling. If there's deviation in a critical zone, the part gets scrapped. The rejection rate when developing a new casting type runs from 10 to 20%. In mature production, 2 to 4%. Doesn't sound like much, but every rejected part means $250 to $400 of aluminum going back to the melting pot. Heat treatment after casting isn't optional, it's mandatory. The part goes into the furnace for solution annealing at temperatures between 1850 and 1900 degrees Fahrenheit for 2 to 3 minutes, then water quenching, then artificial aging at 350 degrees for 4 to 6 hours. This sequence transforms the aluminum from its as-cast state into one where it's simultaneously strong and ductile. Tensile strength roughly doubles compared to untreated castings, from 25 to 30,000 pounds per square inch, up to 45 to 50,000. That's comparable to sheet steel, but at 30 to 40% less weight. Coming out of the heat treatment oven, the part heads to machining, milling of mating surfaces and drilling holes for suspension mounts, battery packs, and body panels. Precision here is plus or minus 0.02 of an inch on datum surfaces. Then laser measurement of geometry at 120 to 200 control points. If the part warped during heat treatment more than 0.03 from the reference, it goes for rework or gets scrapped. Why are only a few factories in the world doing this right now? First, the press itself. Made by 1 or 2 companies globally, the wait for a new machine, anywhere from 80 months to 2.5 years. Price tag, $50 to $80 million a unit. Second, the building. A press like this needs a facility with ceiling height no less than 40 feet and flooring that can handle loads from 800 to 1,200 tons on the support pad. Building such a facility from scratch, another year to 18 months and $30 to $50 million. Third, people. An operator for this press goes through 6 to 12 months of training, and an experienced technologist who knows how to dial in casting parameters for a new alloy and new geometry. That's someone who simply isn't available on the open job market. I watched the press open after its cycle, and a robotic arm pulled out a casting the size of a bed. The part is still steaming. It's hot, around 500 degrees Fahrenheit, and grey. And in this single part, every bracket is already built in. Every structural rib, every mounting point. 240 pieces, now 1. 80 welding robots, not needed. This is why electric truck manufacturers are willing to pay $80 million for the mold and another $80 million for the press, because if they don't do it, someone else will, and then their vehicle's production cost will be $3,000 to $4,000 less than yours. In a business this competitive, that's a death sentence. Subscribe. The next project is already in the queue, and it's going to be even bigger. Drop a comment telling me where you're from. Maybe next time I'll come to you. Your house has no electricity. Your phone doesn't exist. The internet is physically impossible. Electric motors of any kind can't be built. And human civilization is frozen in the 1800s with steam engines and gas lamps. All because we never figured out how to refine one reddish metal that conducts electricity better than anything else except silver, which costs 50 times more. Without this metal, every wire would need to be 3 times thicker and cost 4 times as much. Power grids couldn't reach beyond cities. Your electric bill would be $1,200 monthly. Today, we're going inside the factory in Utah, where this metal gets refined to 99.99% purity, and I'll show you why that purity matters, and what would happen if we used something else instead. The Kennecott Copper Refinery in Magna, Utah, sits 12 miles west of Salt Lake City, and has processed copper continuously since 1903. This facility receives ore from Bingham Canyon Mine 20 miles south, the largest man-made excavation on Earth visible from space. The refinery processes 300,000 tons of copper per year, and every step creates properties that make electrical civilization possible. Raw copper ore contains only 0.6% actual copper mixed with rock and minerals. If copper was never discovered, we'd use aluminum for electrical wiring. Aluminum conducts only 60% as well as copper, meaning you need 50% more cross-sectional area for the same current. Every wire in your house would be thicker and heavier. Building construction costs would increase 30% just from wiring. The first stage crushes ore into powder and mixes it with water and chemicals in flotation tanks. Air bubbles blow through, and copper minerals stick to bubbles and float as froth while waste rock sinks. The froth contains 30% copper, a 50-fold increase from raw ore. This concentration matters because copper's conductivity depends entirely on purity. Even tiny impurities dramatically increase resistance. 1% phosphorus increases resistance by 50%. 0.1% arsenic doubles it. Without purification, we'd use metals that lose huge amounts of energy as heat. Power companies would generate 3 times more electricity just to compensate for transmission losses, 3 times more power plants, fuel, and pollution. Concentrated ore moves to the smelter and heats to 2,200 degrees Fahrenheit. Copper melts and separates from sulfur and iron, which become slag. What emerges is blister copper at 98% purity. Better, but not good enough for electrical use. Copper's heat tolerance becomes important here. It carries high currents without melting, doesn't melt until 1,984 degrees Fahrenheit. Aluminum melts at only 1,221 degrees. In electric vehicle motors or transformers, aluminum would literally melt under load. Electric motors would need to be 3 times larger to keep current densities low enough. A 200-pound copper motor would weigh 600 pounds in aluminum and deliver less power. Blister copper moves to electrolytic refining, the most critical stage. Impure copper sheets become anodes in giant tanks with acidic copper sulfate solution. Pure copper cathodes sit opposite, and when current passes through, pure copper ions migrate to cathodes while impurities fall to the bottom. After 12 days, cathodes are coated with 99.99% pure copper. This extreme purity creates extreme conductivity. At 99.99%, copper conducts so efficiently that a mile-long wire loses only 2% power as heat. At 98% pure, that wire loses 15%. With aluminum at any purity, you lose 5 to 8%. The United States has over 600,000 miles of high-voltage transmission lines. If those were aluminum instead of copper, we'd lose 200 billion kilowatt-hours per year in transmission, enough to power 20 million homes. your electric bill would triple. Pure copper cathodes get melted and cast into forms. Some become wire rod drawn through progressively smaller dies, creating wire from thick power cables to hair-thin magnet wire. Others get rolled into sheets for circuit boards and building materials. Each application requires different properties, but all depend on 99.99% purity. Copper's combination of conductivity and ductility becomes critical here. Copper can be drawn into micron-thick wire without breaking. Aluminum is brittle. When you bend aluminum wire repeatedly, it cracks. This is why every electric motor uses copper windings. The wire bends around tight curves hundreds of times during manufacturing without breaking. Without copper, we couldn't mass-produce electric motors. No motors means no electric vehicles, power tools, washing machines, fans, or pumps. Every copper batch goes through rigorous testing, and there's a specific reason purity standards are so strict. During the 1960s and early 70s, copper prices spiked, and builders used aluminum wiring in homes to save money. Aluminum was cheaper, but had higher resistance, running hotter under load. The real problem was connections. Aluminum expands and contracts more than copper when heating and cooling. Over months of electrical cycling, aluminum wire worked loose from connection points. Loose connections create more resistance and heat. The insulation would char and ignite. Between 1965 and 1973, tens of thousands of house fires traced back to aluminum wiring. Dozens died. Insurance companies refused to cover homes with aluminum wiring. That crisis proved copper can't be substituted. Today, every copper product goes through conductivity testing. Pure copper at 20 degrees Celsius has conductivity of 58 million Siemens per meter. Anything below 57 million gets rejected and reprocessed. They also do bend testing, thermal cycling, and microscopic inspection. The rejection rate is 6%. Copper that passes inspection ships to manufacturers making electrical wire, motors, and electronics. Kennecott produces 300,000 tons yearly, but global production is 25 million tons because demand is enormous. Without copper, no electrical grid exists as we know it. Thomas Edison tried iron wire for electrical distribution in the late 1800s. It didn't work. Resistance was so high that power couldn't travel more than a few blocks. Without copper, electrical power is limited to buildings with their own generators. No power lines between cities. Every building needs its own coal or diesel generator running constantly. The internet is physically impossible. Fiber optics carry data long distances, but electronics at each end require copper for power and short-range transmission. Data centers use thousands of miles of copper cabling. Without copper, you might have mechanical telegrams, but no electronics, computers, or digital communication. Electric motors don't exist in practical form. Every motor requires copper windings for electromagnetic fields. Aluminum motors are 3 times larger for the same power, overheat easily, and fail quickly. Without copper motors, manufacturing never industrialized beyond steam power. Modern factories don't exist. Every product is more expensive because it's made by hand. Transportation is completely different. No electric trains. You're stuck with diesel locomotives. No electric cars. Tesla doesn't exist because you'd need a 6,000-pound aluminum motor to move a 2,000-pound car. Ships use massive diesel engines instead of efficient electric systems. You've seen how copper ore concentrates from 0.6% to 30% through flotation, how 2,200 degree smelting separates copper from impurities, how electrolytic refining creates 99.99% purity, making efficient electrical transmission possible, and why the aluminum wiring crisis proved copper can't be substituted. If this interested you, subscribe for more deep dives into materials making modern life possible. Thanks for watching. So, I know North Carolina doesn't sound particularly exotic, but what's being made here flies at 66,000 feet above the Pacific Ocean and keeps 400 passengers in the air at the same time. This is the factory that produces blades for the GE9X turbine engine series, the largest commercial jet engines in the world today. One of these engines weighs about 9 tons, generates thrust up to 105,000 pounds. Sorry, that's roughly 460 kilonewtons, and costs around $50 million. But we're not here because of the engine. We're here because of one specific part that's about the size of your palm and costs more than a nice car. A turbine blade. In the hot section of the engine, in what's called the high-pressure turbine, there are between 160 and 180 of them per wheel, depending on the stage. Each one weighs roughly 10.5 to 14 ounces. But the conditions it operates in, this isn't engineering anymore. It's straight up torture for common sense. The temperature of the gases flowing around the blade during engine operation, 2700 to 2900 degrees Fahrenheit. That's higher than the melting point of steel, higher than the melting point of the very material the blade is made from. How it doesn't just melt, I'll tell you in a minute, because it's one of the coolest things I saw at this facility. The blade material is a nickel-based superalloy. The exact recipe is classified, and they didn't tell me the full breakdown, which is fair. But the general principle is known. Each element is responsible for something specific. Take rhenium, for instance. It provides heat resistance and slows down creep. That's when metal under prolonged stress and temperature deforms completely. The raw material cost for a single blade runs from 200 to 300 euros just for the metal, before anyone's even touched it. Now, how it all begins. The blade manufacturing process is investment casting, also known in the industry as lost wax casting. First step, the wax model. An exact replica of the future blade, including all internal channels, is created from wax under pressure in a metal mold. The precision of this mold, plus or minus 20 micrometers. That's about a quarter of the thickness of a human hair. If the mold deviates any more than that, it goes back for refinement. But the wax model is just the outer form. Inside the blade, there are also cooling channels, thin, winding tunnels through which cold air from the compressor gets pumped during engine operation. That's why the blade doesn't melt, even though the surrounding gas is hotter than its own melting point. Inside, air at temperatures of 500 to 600 degrees Celsius flows through and keeps the metal in the working zone. These channels are formed separately, using ceramic cores that get inserted into the wax model before casting. The core looks like a thin, sturdy comb, and it occupies exactly the space where the channel will eventually be. The wall thickness between the blade's outer contour and the internal channel ranges from 1 to 2 millimeters. Any thinner, and the blade becomes brittle. Any thicker, and the cooling can't keep up. Next, the wax model gets dipped into a liquid ceramic slurry and coated with fine ceramic sand. Dip, pull out, dry, and repeat the cycle 8 to 12 times. Each layer dries for 4 to 8 hours. After the final layer, you get a ceramic blob about 10 millimeters thick, hard, rough to the touch, kind of like papier-mâché if papier-mâché were made from space shuttle material. Then this whole thing, with the wax still inside, goes into an autoclave, where at temperatures around 300 degrees Fahrenheit and elevated pressure, the wax melts out through a small opening. Hence the name, lost wax casting. What's left inside is a perfect negative of the blade shape. The ceramic holds its form, the cores stay in place. Now comes the metal pour. This is the part I came for. The molten metal gets heated to around 2500 to 2700 degrees Fahrenheit and poured into the ceramic mold. But they don't just pour it and wait for it to solidify. The mold gets slowly withdrawn from the heating chamber at a rate of about 1/10 to 1/5 of an inch per minute. That withdrawal speed controls how the metal crystallizes. If everything's done right, the entire blade, from root to tip, becomes a single crystal. Not a single grain boundary throughout the entire volume of metal. That's single crystal casting. Grain boundaries, the weakest spot in any metal. That's where cracks start under prolonged stress and heat. If there's only one grain, there's no boundary, no failure points. Heat resistance jumps roughly 30% compared to ordinary polycrystalline casting. After cooling, they break the ceramic shell, just mechanically, with hammers and vibration. Out comes a gray blade with ceramic cores inside. The cores come out in an alkaline solution at roughly 210 degrees. The chemistry dissolves ceramic, but leaves the metal untouched. This takes 4 to 8 hours. After washing, those same cooling channels remain in the center, clean, precise, completely open. Then they check the blade. X-rays reveal pores and cracks inside the metal. Fluorescent liquid catches surface defects. A special probe passes through each cooling channel, verifying it's not blocked by ceramic residue. If even one cooling channel is partially blocked, the blade goes straight to scrap. Not to rework, straight to scrap. Because you can't fix that. The rejection rate at this stage runs 2 to 5% per batch. Doesn't sound like much, but given what each part costs, we're talking real money. After inspection, heat treatment. The blade goes through multiple temperature cycles. First, around 1900 degrees for several hours, then a gradual cool down. This process evens out the internal stresses that formed during casting and locks in the alloy's microstructure. The exact heat treatment protocol? Also classified. When I asked, the manager who was walking me through just smiled and changed the subject. Final stage, protective coatings. First comes a metallic bond coat, nickel and aluminum based, applied using a plasma spray process. That's the foundation. On top of that goes the thermal barrier coating, zirconia stabilized with yttrium. It's ceramic, and it's that ceramic layer that absorbs the first several hundred degrees from the screaming hot gas stream. This layer is between 100 and 2 micrometers thick. The application looks like spray painting in a chamber. The blade rotates, the plasma gun moves along it, following a preset path. But the temperature of the plasma stream during application is around 18,000 degrees Fahrenheit. For comparison, the surface of the sun is about 10,000 degrees. So the tool is nearly twice as hot as a star, but the blade itself doesn't heat up more than 4 degrees, because the entire process is incredibly fast and incredibly precisely controlled. The finished blade goes for final weighing, measurement, and registration. Each one gets an individual serial number and a passport where all parameters are recorded, from the chemical composition of the melt to the results of every control measurement. This document is kept for as long as the engine lives, and that's 20 to 30 years and tens of thousands of flight hours. On my way out, I asked how many blades they made per month. They told me it was in the range of several thousand units across all sizes. They wouldn't give me an exact number. But when you consider that one engine needs several hundred hot section blades alone, and orders for the 9X remain backed up for years ahead, you can imagine the scale. You're the best. Subscribe so you don't miss the next facility. It's going to be even more interesting. Write in the comments where you're from, and maybe next time I'll visit your city. What if I told you that a high-speed train wheel experiences temperatures hot enough to make metal glow, and still can't afford to fail? Why must this piece of steel withstand tests that would destroy any car wheel in seconds? There's a reason almost nobody suspects, and if you stay with me through to the finale, you'll discover the secret process that forces the wheel to survive where other metal simply melts. But first, tell me, does your country actually manufacture railway wheels, or are they imported? A train rockets down the tracks at over 186 miles per hour. At that speed, an ordinary wheel would simply disintegrate. Why? Because it has to withstand not just weight, but a whole series of inhuman trials. The material is everything. This isn't ordinary steel used for silverware or even car bodies. High-speed train wheels are made from a special grade of steel, melted according to a unique, meticulously refined recipe. This recipe is a combination of iron with specific alloying elements, manganese, silicon, chromium, molybdenum, that give the steel extraordinary strength, toughness, the ability to absorb impacts without failing, and endurance. Beyond that, this steel must be as pure as possible, free of any foreign impurities that could become a weak point. After the special steel is melted in massive metallurgical furnaces, it's poured into molds to create large steel billets, what we call slabs or blooms. But that's just the beginning. The real transformation starts in the forging shop. This is where one of the most powerful forging presses comes into play, along with specialized forging machines. The billet, heated until it glows bright yellow or red, that's around 2000 degrees Fahrenheit, is fed under the press. The process involves multi-stage forging. It's not a single strike, but rather a whole series of controlled pressures and rotations. The giant hammers, or jaws of the press, slowly, yet with unstoppable force, flatten and shape the red-hot metal. First stage, the billet is compressed to give it a rough circular shape, densifying the metal and eliminating internal voids. Second stage, the material is flattened and rolled, forming a disc with a central hole. This is where the future wheel's outline begins to emerge, with its rim, disc, and hub. This directional metal flow shapes its internal fibrous structure, making the wheel exceptionally strong in the required directions. Forging, unlike casting, transforms steel's microstructure. It compresses the metal's grains, eliminates casting defects, and creates a directional fibrous structure that gives the wheel exceptional strength and fatigue resistance. It's like an athlete's muscles. After training, they become stronger and more resilient. Why such complexity? Because high-speed train wheels operate under extreme conditions that are hard to imagine. When moving at speeds over 186 miles per hour, the wheel's surface heats up from friction against the rails and brake pads to nearly 2000 degrees Fahrenheit. That's the temperature at which metal begins to glow red and change its properties. And this heating isn't constant, it's cyclical. Heating during acceleration and braking, cooling during movement. The material must withstand these constant temperature fluctuations without forming microcracks, which over time can lead to failure. Each pair of wheels carries a load of dozens of tons. A single railcar can weigh between 50 and 70 tons, and this weight is distributed across just 4 wheels, that is, 2 wheel sets. This creates constant pressure acting on the wheel. The train doesn't ride on a perfectly smooth surface. It crosses rail joints, uneven sections, and switches, which generate continuous impact loads. The wheel must be incredibly tough to absorb these shocks without cracking or breaking apart. After forging, the wheels aren't finished yet. They undergo complex heat treatment, which is key to developing their final properties. The wheel centers, the discs that connect the hub to the rim, are hardened. Hardening is a process of heating steel to high temperatures, then rapidly cooling it. This makes the metal harder and stronger. But hardening makes the metal brittle, so it's always followed by tempering, reheating to a lower temperature with slow cooling. Tempering reduces brittleness and improves toughness while maintaining high strength. This combination of hardening and tempering creates the ideal steel microstructure that can withstand extreme operating conditions. But even after all these complex processes, no wheel reaches the rails without brutal yet necessary testing. Every single wheel, without exception, undergoes ruthless inspections. Ultrasonic testing. It's like medical ultrasound diagnostics, but for metal. Special sensors send high-frequency ultrasonic waves through the wheel. If there's even a microscopic crack, void, or defect inside, the ultrasonic wave bounces off it and creates an echo that the instrument captures. This method allows us to see internal defects without destroying the wheels. A defect the thickness of a human hair is already grounds for rejection. Magnetic particle inspection. The wheel gets magnetized, then its surface is coated with fine ferromagnetic powder. If there's a crack, even one invisible to the naked eye, it distorts the magnetic field, and the powder concentrates along that crack, making it visible. This reveals even the tiniest surface defects that could become failure points during operation. Only wheels with perfect structure and 0 defects are cleared for installation on high-speed trains. This isn't engineering perfectionism. It's about the safety of thousands of passengers who trust their lives to these metal giants. While the United States isn't leading high-speed rail development like China or Japan, its rail network remains one of the world's largest, and American manufacturers have extensive experience producing high-quality wheels for various rolling stock, passenger trains, freight locomotives, and switching equipment alike. Unlike the automotive industry, where thousands of companies manufacture parts, the railroad wheel manufacturing market in the US is significantly more concentrated. This is a highly specialized field, requiring massive investments in metallurgical equipment, forging presses, and quality control systems. The two main and most powerful players in the North American railroad wheel manufacturing market are Amstead Rail and KF USA. While KF is a Spanish company, it maintains production facilities in the United States to meet local demand. Previously, other major manufacturers existed, but the market has consolidated. Total annual railroad wheel production in the US fluctuates, but can be estimated in the range of 300,000 to 500,000 units per year. This figure includes wheels for all types of rolling stock. It's worth noting that while the US can manufacture wheels capable of withstanding high speeds, the actual demand for wheels designed for continuous operation above 186 miles per hour remains relatively limited due to the scarce number of true high-speed rail lines in the country. For instance, Amtrak's Acela Express trains, running along the Northeast Corridor, reach speeds up to 150 miles per hour on certain segments, but not beyond the aforementioned threshold of 186 miles per hour, which requires specific material and design standards. However, US wheel manufacturing technologies and standards do enable production that meets international requirements for high-speed trains should the need arise. From a material standpoint, American manufacturers, like their global counterparts, utilize specialized grades of carbon steel alloyed with manganese, silicon, and other elements to achieve the necessary strength, wear resistance, and toughness. Forging, heat treatment, and non-destructive testing processes are standard and comply with the highest international safety and quality benchmarks. Every year, machines are built around the world so massive and powerful that a single one could supply electricity to an entire city, and costs as much as dozens of private jets. But what if I told you that inside this colossal structure, there are parts machined with precision, thinner than a human hair, and that one tiny mistake could cost millions of dollars or even destroy everything? Today we're going inside a place almost no one gets to see, the heart of turbine manufacturing. And trust me, what you're about to see will completely change how you think about engineering, if you stick around till the end. Let's start with the fact that there are two main types of these turbines, and they work on very different principles. First, the steam turbine. You'll find these at nuclear and thermal power plants, on massive tankers and icebreakers. Second, the gas turbine. It's more like a giant jet engine without wings, and lives mostly at gas-fired power plants and on some military vessels. Here at the factory they make both types, but we're heading first to the steam ones, because they're older, more massive, and look like they were invented 2 centuries ago. Which, actually, they were, but they're still very much around. How a steam turbine works: short and formula-free. There's a boiler that heats water into pressurized steam at anywhere from 800 to 3,000 pounds per square inch. This steam, hot, pressurized, angry, blasts through nozzles onto rotor blades. The blades start spinning. The rotor spins the shaft. The shaft spins a generator or a ship's propeller. The steam cools down, condenses back into water, and returns to the boiler. The cycle is closed. Sounds simple, but for this simple not to explode into pieces and to run for 3 years without major repairs, you need all of this around me. The first shop they take me to is the Foundry. This is where every turbine begins. The casing, the outer shell that holds all the internal components under pressure, is cast from alloy steel or cast iron, depending on operating parameters. For steam turbines in large power plants, the casing is cast in 2 or 3 tiers, and each tier is a separate mold. The mass of 1/2 of a casing can reach 60 to 80 tons. The metal is melted in arc furnaces with a capacity of 50 to 150 tons of molten metal, and the temperature there is around 5,000 degrees Fahrenheit. The mold for a large casing is a pit in the floor, 6 to 10 feet deep, lined with refractory clay. The metal is poured through a system of channels, and the entire process of filling one large mold takes 15 to 30 minutes. Then the casting cools, naturally from several days to 2 weeks, depending on the mass. After cooling, the casting goes to its first inspection. Ultrasonic testing searches for voids and inclusions inside, spots where the metal didn't fuse the way it should. X-rays check critical zones. If they find something significant, the casting goes back to remelt. No compromises. The rejection rate at this stage runs 3 to 8% depending on the casting's complexity, and that's completely normal for parts this size. Next, machining. Now, here in the shop floor, there are machines that made my jaw drop. The horizontal boring mill that machines the inner casing surface. It's about 60 feet long. The table where the part sits moves. The spindle stays put. The tool freely bores the bearing and seal mounting surfaces to an accuracy of plus or minus 0.5 of an inch. Why so precise? Because the rotor spinning inside at 1500 to 3600 revolutions per minute has a clearance between its blades and the casing of 50 to 150 microinches. 1% efficiency loss at a large power plant. That's millions of dollars in extra fuel costs per year. The rotor is the star of this story. It's a shaft carrying discs with blades, and it's the most complex part of the entire turbine. The shaft for a large steam turbine is a forging made from special chromium molybdenum vanadium steel, 20 to 40 feet long and weighing 20 to 60 tons in its rough state. A forging means you take a red-hot ingot of metal and just hammer it with a press weighing 5,000 to 50,000 tons to give it the shape you need. The grain structure of the metal during forging gets oriented along the shaft's axis. That's how you achieve torsional strength. After forging, the shaft goes through heat treatment again, then heads to the machine shop. Turning takes 2 to 4 weeks of continuous work on a lathe that's nearly 70 feet long. Chips fly, coolant flows, and machining away from that massive blank reveals the sleek shaft you saw in the drawings. This is the part where I'm always amazed. A gigantic component, yet precision like a watch mechanism. Blades are a separate production line. Steam turbines at large power plants have anywhere from 8 to 20 stages, and each stage is a disc with blades. First stage blades are small, sometimes less than 2 inches tall, because the steam there is still under high pressure and dense. Last stage blades are massive, up to 5 or 6 feet long on the largest turbines. These blades are forged and milled from iron-based alloys or stainless steel, and in their final profile, they have an aerodynamic shape with precision to within plus or minus 0.002 of an inch along the entire length. Each blade is checked for resonant frequency. It can't match the operating rotational frequency of the rotor, or else after a few thousand hours, a fatigue crack will develop from vibration. How they test this is simple. They tap the blade with a small hammer and listen with a special acoustic sensor. A very elegant method for such a serious problem. Assembling the rotor. This is when it starts to feel like an operating room. Bladed discs get mounted onto the shaft using shrink fitting. The disc gets heated to 300 to 400 degrees Fahrenheit. It expands, slides onto the shaft, then cools and grips the shaft with a force no bolt could ever match. No threads, no glue, just temperature difference and precision sizing. The interference fit when cold, 1 to 3/1000 of an inch per inch of diameter. After assembly, the rotor gets balanced, and this takes 1 to 3 days. Balancing happens on a specialized rig, where the shaft spins on bearings while sensors register vibration. If there's any imbalance, metal gets removed from certain spots, or balancing inserts get installed. Allowable residual vibration on a large rotor, fractions of an ounce per inch of radius. If you think that's strict, you're thinking right. After assembly, the turbine heads to the test stand. At full operating parameters, pressure and temperature, they run the turbine for 24 to 72 hours. Sensors track bearing temperatures, vibration, steam leaks, power output. If anything goes outside the limits, stop, disassemble, analyze. There have been cases where they found a defect here that the X-ray missed initially. So the test stand isn't just a formality, it's the last line of defense before shipping. The finished turbine gets broken down into transport blocks, casing separate, rotor separate, auxiliary equipment separate. A large turbine rotor travels on a special trailer with hydraulic suspension, the kind you've seen on YouTube, with 18 axles moving at 20 miles per year. They coordinate the route a month in advance. Every bridge height and every turn width needs checking from the factory to the port or customer. Sometimes for one of these transports, they temporarily remove road signs and even take down power lines over the highway. I asked the chief engineer how many turbines they build per year. He said 12 to 20 of various types. That's it. Less than 2 per month. But each one runs for 30 to 50 years and generates electricity for hundreds of thousands of people every day. Some things don't need high-volume production. What if the metal that still powers most cars on the planet has been quietly poisoning people since the days of the Roman Empire? And we found out too late. Lead built aqueducts, adorned the faces of Egyptians, and today hides in billions of lead-acid batteries, without which cars, elevators, and entire cities would grind to a halt. We'll descend into mines where explosives shatter rock, trace the journey of galena to red-hot furnaces, and discover why this metal simultaneously saves infrastructure and destroys health. Stick around till the end. One fact about lead will forever change how you look at an ordinary battery. Okay, let's rewind the clock and dive into a story that began long before the first smartphones and even before the invention of the wheel. How did people even learn about lead, this sneaky, two-faced metal? Truth is, nobody knows exactly who or when first discovered lead, because it wasn't officially discovered by a scientist in a lab like many other elements. Lead is one of those metals that's just always been around humans, and its history is intertwined with the history of civilizations themselves. Picture this: ancient times, way before people learned to work with iron, or even copper. They were searching for interesting stones, clay, anything they could use. And then, in certain places, especially where there are ore deposits, they stumbled upon a really unusual stone. These were lead ores, most commonly galena, lead sulfide, which looks like dark gray, almost black crystals with a metallic shine, often in cubic shapes. Lead ores often lay close to the Earth's surface, and there was plenty of it around. Plus, lead sometimes occurs in its natural, pure form, though that's pretty rare. Lead has an incredibly low melting point, just 621 degrees Fahrenheit. This means you didn't need some super high-tech furnace to melt it down. A good hot campfire was enough, and if there happened to be lead ore nearby, shiny liquid metal could literally just melt right out of it. The metal in the ore heats up, melts, and starts flowing out of the rock, forming little shiny puddles or droplets. This must have been absolutely mind-blowing to witness. Out of stone, without any tools, just from fire alone, this shiny, heavy, soft material appears that you can shape with your hands. You could easily flatten it, bend it, cut it even with primitive tools. It wouldn't break like stone. This made it perfect for crafting simple objects. Archaeological findings show that lead was used as far back as 7,000 or 8,000 years ago, dating to the Neolithic period, for example, in Turkey. People found beads and other small lead objects there. In Mesopotamia, Egypt, and later in Greece and Rome, lead became widespread due to its availability and ease of working with. The Romans built their famous aqueducts and water supply systems using lead pipes. The word plumbing comes from the Latin plumbum, which means lead. Ancient Egyptians used lead sulfide for eye makeup, while Romans used it for skin lightening and in paints. Nobody back then, of course, suspected this metal was toxic. After all, lead poisoning symptoms were often chronic, developed slowly, and could easily be blamed on bad luck, other illnesses, or curses. People just saw a shiny, useful metal that was easy to work with, and they actively used it, never suspecting that beneath its appeal lurked a treacherous enemy. Now that we know the grim history of lead's discovery, let's fast forward to our time. Despite all its toxicity and the massive campaign to phase it out, lead is still part of modern industry. But how is it mined now, and where does it hide when we're so desperate to get rid of it? This is a story about precision, control, and the constant battle against its poisonous nature. Lead, like its neighbor zinc, is rarely found in its pure form. It's mostly extracted from ores, where it exists as lead sulfide, known as galena. And, as you might have already guessed, this anti-hero often shares its deposits with zinc, as well as other valuable metals like silver and copper. The world's top lead producers are China, Australia, the United States, and Peru, which once again overlaps with the geography of zinc mining. The extraction process starts with locating ore bodies. Geologists, armed with cutting-edge technology, scan the ground and conduct exploratory drilling to find spots where galena concentrations make economic sense. Once a deposit is identified, mining operations begin. This can either be an open-pit mine, where massive excavators strip away the top layers of earth, gradually working their way down to the ore, or an underground mine, where miles of tunnels are drilled, penetrating deep into the Earth's crust. In underground mines, drilling rigs are used to create holes in the rock, which are then packed with explosives. After controlled blasts that break up the ore vein, specialized loaders gather the ore fragments and haul them to the hoisting shafts. Ventilation systems run at full capacity, removing dust and pumping fresh air down into the depths. All the ore is brought to the surface, where it begins its long journey to becoming a metal ingot. After crushing, the flotation process kicks in. This is a chemical-physical method that separates different minerals. The crushed ore is mixed with water and special reagents in massive tanks. These reagents selectively attach to galena particles, making them water repellent. Then air is pumped through the mixture, creating bubbles that the lead mineral particles cling to and rise to the surface as foam. This foam is collected, forming lead concentrate. The waste rock settles at the bottom and gets disposed of. Since lead and zinc are often found together, different reagents and flotation cycles can be used to separate them individually, which requires high precision and chemical control. The resulting lead concentrate, now containing a much higher percentage of lead, is shipped to the metallurgical plant. This is where it transforms into pure metal. The most common method is pyrometallurgy, which involves several stages. First, the concentrate is roasted in special furnaces at high temperatures. This is a calcination process that removes sulfur from galena, converting it into lead oxide. The sulfur that's released as sulfur dioxide gas is carefully captured and converted into sulfuric acid to prevent air pollution. Then the lead oxide is loaded into large blast furnaces, where it's mixed with coke and fluxes. In these furnaces, at temperatures over 2,000 degrees Fahrenheit, a reduction process takes place. The carbon from the coke pulls oxygen away from the lead oxide, releasing liquid metallic lead. The molten lead, which is extremely heavy, settles to the bottom of the furnace. On top, a layer of slag forms. That's the melted impurities. Molten lead is periodically drained from the furnace, but this isn't pure lead yet. It contains impurities of other metals, such as copper, silver, gold, bismuth, and nickel. That's why lead goes through one more stage, refining. This could be heating to specific temperatures to remove impurities, or electrolytic refining, where electric current separates lead from other metals, achieving very high purity. It's at this stage that valuable byproduct metals like silver and gold, which accumulate in lead ores, are extracted. So where is all this carefully mined and refined lead being used today, now that we know about its dangers? The biggest consumer of lead, accounting for about 85% of all global consumption, is the production of lead-acid batteries. These are the same batteries that start the engines in nearly every car on the road, and they're also used in uninterruptible power supplies, backup power for telecom networks, and large-scale energy storage systems. In electric vehicles, even though the main battery is lithium-ion, there's often still a small 12-watt lead-acid battery to power the onboard electronics. This is a massive market that keeps demand for lead rock solid. 70% of the plastic you toss in the recycling bin ends up straight in a landfill. Not because you're doing something wrong, but because traditional recycling only wants clean, single-type plastic. Everything else, dirty packaging, films, toys, shoe soles, not its problem. But there's a technology that takes any dirty, mixed plastic and turns it back into oil. No burning, no oxygen. I just visited one of only 25 facilities like this in the entire world, and I'm going to break down exactly how it works. From a pile of trash to a barrel of synthetic oil. Plus, one number from the director that makes it crystal clear. Even this is just a drop in the ocean. Regular plastic recycling, the kind you know from those triangle bins, it's super picky. It wants plastic to be one type, clean, no caps, no labels, no food residue. Plastic bottles, separate. Polyethylene, separate. Polystyrene, they often refuse to take it at all. And anything that doesn't meet these criteria, which is roughly 70% of all plastic that ends up in the trash, goes straight to the landfill, or gets burned. All that dirty food plastic, multi-layer chip bags, toys, shoe soles, films, traditional recycling doesn't want them. And that's where a different game begins. What they do at this facility is called chemical recycling, or plastic pyrolysis. And the principle is so simple, at first you don't even believe it. They take plastic and heat it without oxygen to temperatures between 550 and 900 degrees Fahrenheit. At that temperature, the long polymer chains. And plastic, if we're being brief, is just very long chemical chains, break apart into short fragments. These fragments escape as vapor, enter a condenser, cool down, and turn into liquid. This liquid is pyrolysis oil, or synthetic crude oil. The exact same product that's the starting point for making plastic, gasoline, chemicals. The circle is complete. But the gap between theory and what happens here in practice? Wide as Texas. First problem, raw materials. The plant processes anywhere from 150 to 200 tons of mixed plastic every single day. I saw this pile. It looks like where all your plastic bags, disposable lids, and thermos caps go to die. Before any of this hits the reactor, it goes through sorting, cameras, magnets, air separators. Metal has to come out completely because it just won't break down in the reactor and it clogs the equipment. Chlorinated plastics, for example, have to be separated out because when heated, they release hydrogen chloride, which literally eats the reactor from the inside. One poorly sorted container can shut down the entire line for days and cost the plant tens of thousands of dollars in repairs. After sorting, the plastic gets cut into pieces roughly 1 inch by 1 inch. This ensures even heating in the reactor. The shredders here are the size of a bus and chew through everything with a sound that makes you want to jam in earplugs and drive home. Then these pieces get fed into the reactor by an auger conveyor. The reactor, that's the key piece, and all the complexity revolves around it. It's a massive steel cylinder. This facility has 6 of them, each as tall as a 3-story building. And inside, a complete absence of oxygen is maintained. This is critical. If oxygen gets in at these temperatures, you won't get pyrolysis, you'll get ordinary combustion. Basically, a fire inside. That's why before feeding in the plastic, the system is purged with nitrogen, replacing the air with an inert gas. Oxygen sensors are mounted on every flange, and if the level rises above 0.5%, the line shuts down automatically. At 750 degrees Fahrenheit, polymer chains start breaking apart. Polyethylene, polypropylene, polystyrene, they all have different cracking temperatures, different reaction rates, different product yields. That's exactly why mixed plastic is so tricky. If you fed only pure polyethylene into the reactor, you'd get a stable 80% oil yield by weight of feedstock. With mixed plastic, that number bounces between 50 and 65% depending on batch composition. And there's no way to predict more accurately without chemical analysis of every ton. And that kind of analysis costs money. Real money. The vapor coming out of the reactor is a mixture of hydrocarbons of different sizes. It passes through a fractionation column where it separates by boiling point, almost like at a regular oil refinery. The lightest fractions are gases. They don't condense and get burned immediately in a burner to produce heat that's fed back into the reactor. At this stage, the plant is practically energy self-sufficient. It heats itself with its own gases. The middle fractions remain as pyrolysis oil, a dark, slightly viscous liquid that smells roughly like you threw a plastic bottle on a campfire and let it burn completely. The heavy fractions settle out as fuel oil or a waxy substance. And there's still a solid residue left over, carbon black or technical carbon. It gets pressed into pellets and sold to manufacturers of rubber products or pigments. There's another technical hurdle worth explaining: chlorine. Chlorine actually hides in a ton of different packaging, in dyes, additives, adhesives. When plastic with chlorine gets into the reactor, the chlorine reacts with water and forms hydrogen chloride, an extremely aggressive acid. It eats through the steel reactor walls from the inside in about 6 to 12 months instead of the projected 10 to 15 years. Replacing a single reactor costs several $1,000s and weeks of downtime for the entire production line. So chemical analysis of incoming plastic and chlorine monitoring is literally a matter of plant survival. While I was walking through the facility, one detail struck me: sensors everywhere. On every pipe, every valve, every welded joint, there are sensors for temperature, pressure, and gas composition. This entire system feeds into a central control room where 3 operators watch screens displaying roughly 300 parameters simultaneously. If pressure in any reactor jumps above the calculated value by more than 5%, an automatic valve releases the excess. If temperature drops below 2.5 degrees, cracking quality decreases and the oil comes out heavier. That's bad. If the temperature exceeds 900 degrees, gasification kicks in. Oil yield drops to 0, and all you get is gas and carbon. The window between normal and something went wrong? Literally 50 degrees. In a reactor the size of a house. The pyrolysis oil produced here gets shipped in tankers to petroleum refineries, where it's blended with regular crude and goes through cracking, turning into naphthene and xylene, which are feedstocks for making new plastic. So theoretically, a shampoo bottle could circle back to polypropylene pellets and become a new bottle. Some major chemical companies, including several from the global top 10, are already buying this oil to manufacture plastic, and even paying a premium over conventional petrochemical feedstock, because they can print "made from recycled plastic" on the packaging, and for them, that's a marketing asset. The plant director told me straight up that even if they double their capacity and hit 400 tons a day, they'll be processing less than 0.1% of the world's plastic waste stream. The solution to the problem? Either drastically cut plastic production or build several thousand of these plants across the globe. Right now, neither is anywhere on the horizon. But this plant is proof that mixed plastic pyrolysis technology can actually work at industrial scale and turn a profit, even if it's razor-thin margins with really nerve-wracking logistics. I'm walking out of here with respect for the people doing this work, and a solid sense that 92%? That number's going to stay relevant for a long time. And you know what else is going to stay relevant? Subscribing to my channel. A pinch of metal, a few hundred grams per ton of steel. Add it, and the steel gets 30% stronger. Same weight, same thickness. But it takes a third more force to break it. That pipeline under the North Sea, the one carrying gas at thousands of pounds per square inch. Without this metal, The walls would need to be twice as thick. The project, twice as expensive. Nearly 90% of this metal comes from one country, Brazil, and most of it from one single mine. One company digs it up. One family controls that company. They've been sitting on this for over 50 years without most people ever hearing about it. The metal is called niobium, the quietest monopoly on the planet. But before niobium ends up in a bridge or a rocket engine, it starts as something that looks like ordinary dirt. What happens next involves crushing, floating, and a chemical reaction hot enough to melt through most metals. Araxá, small city in Minas Gerais, Brazil. Population around 100,000. Dusty roads, cattle ranches, a rodeo once a year. But underneath it sits the largest niobium deposit ever found. The mine belongs to CBMM, Companhia Brasileira de Metalurgia e Mineração. Private. The Moreira Salles family holds 70%, one of the wealthiest families in South America. They don't chase headlines. They just dig up most of the world's niobium and ship it out. Here's the thing. This isn't OPEC. No cartel, no politics, no sanctions. Just one company sitting on a geological freak. The pyrochlore deposit, a mineral packed with niobium, is so rich at Araxá that nobody else can compete on cost. Canada mines about 7,000 tons a year. Everyone else splits the scraps. Nobody comes close. And the ore they're pulling out of that pit doesn't look like much. Brown rock. Heavy. But inside that rock sits the element that holds modern infrastructure together. Mining starts open pit. Trucks the size of houses haul pyrochlore ore from benches cut into the hillside. Each load, about 200 tons. The ore contains 2.5% niobium pentoxide. 25 pounds of useful metal per ton of dirt. First step, crushing. The rock goes through jaw crushers, cone crushers, and ball mills until it's a fine, wet slurry. Grey, heavy. Then flotation. The slurry gets mixed with water and chemical agents. Air pumps push bubbles through the mixture. Niobium-bearing minerals grab onto those bubbles and float. Everything else sinks. Workers skim the froth. What comes out is a dark concentrate. About 60% niobium pentoxide. From 25 pounds per ton to 600. Just by letting the right particles float. That concentrate still isn't metal. Turning it into something useful takes one of the most violent chemical reactions in industrial metallurgy. Aluminothermy. Sounds academic. Looks like a war zone. Workers load the niobium concentrate into a steel vessel, packed tight with aluminum powder. Then they light it. Not with a match. With a magnesium fuse that burns at over 3,000 degrees. The aluminum rips the oxygen off the niobium. The reaction hits 4,350 degrees Fahrenheit. The whole charge turns liquid in seconds. No external furnace needed. The reaction generates its own heat. Self-sustaining. The molten mass separates. Niobium iron alloy sinks to the bottom. Aluminum oxide slag floats on top. Workers crack the vessel open and pull out a rough ingot of ferroniobium. 60 to 70% niobium, rest iron. Gray. Dense. Heavy as lead. That ingot is worth roughly $40,000 per ton, and most of it will end up inside steel. Now, why does steel need niobium at all? Because of a trick that engineers stumbled onto, and it changed an entire industry. Microalloying. Add 0.03% niobium to molten steel. 0.03%. A teaspoon of salt in a bathtub full of water. When steel cools, its crystal grains grow. Bigger grains mean weaker steel. Niobium atoms lock into the grain boundaries and stop them from growing. Smaller grains. Tighter structure. 30% stronger. Same weight. The Trans-Alaska Pipeline runs niobium steel. So do gas lines under the North Sea. So does every major bridge built in the last 40 years. And there's a reason this matters beyond construction. SpaceX uses a niobium alloy called C103 for rocket engine nozzles. The exhaust bell on the Merlin vacuum engine, Niobium. It handles temperatures above 2,500 degrees Fahrenheit without deforming. Survives re-entry heat, engine thrust, and vacuum cycling. No other affordable material does all three. Put a number on it. The global market moves over 80,000 tons of niobium a year, worth roughly $3 billion. Almost all of it flowing through one company in Brazil. But ferroniobium is the commodity product. The real money starts when you need pure niobium. And purifying it requires a machine that melts metal with a beam of electrons in a sealed vacuum. Pure niobium. 99.9%. Not an alloy. The element itself. Getting there means electron beam melting. A vacuum chamber. A focused beam of electrons hits the metal hard enough to push temperature past 4,400 degrees Fahrenheit. Niobium melts at 4,474. Most impurities evaporate before the niobium does. The beam sweeps back and forth, melting the bar top to bottom. Impurities leave as gas. Pure niobium collects as liquid, then solidifies. 2 passes. Sometimes 3. Each one cleans it further. The final ingot glows silver gray. Smooth. Dense. And worth 10 to 20 times more per pound than the ferroniobium alloy. That corrosion resistance is why surgeons put niobium implants inside human bodies. Your bone grows around it, and the metal just sits there. Decades. No reaction. Corrosion resistance is useful, but niobium has another property that makes it irreplaceable for the biggest machines in physics. Nothing protects this supply chain. No strategic reserve. No backup that can scale fast. Canada produces about 7,000 tons a year. Everyone else combined barely registers. If CBMM's Erixa operation shut down tomorrow, a flood, a strike, a political crisis, the world would burn through existing stockpiles in months. Steel mills would feel it first. Pipeline projects stall. Bridge construction slows. Then the specialty markets start fighting for scraps. Aerospace. Medical. Particle physics. All clawing at the same shrinking pile. And the strangest part? Nobody talks about it. Niobium doesn't show up on the news. Not on sanctions lists. Not weaponized. China has been prospecting for alternatives. A few junior miners in Africa claim deposits. None of them can match CBMM on cost or scale. The Moreira Salles family runs it like a utility. Stable pricing. Long-term contracts. Quiet enough that nobody bothers looking for a way out. That's the genius of it. The quietest monopoly works because it never gives anyone a reason to break it. Niobium. Named after Niobe, daughter of Tantalus in Greek mythology. Discovered in 1801, ignored for a century. Then someone figured out what a few hundred grams of it does to a ton of steel. And the metal went from a curiosity to a dependency. One mine in Brazil, nearly 90% of global supply, makes steel a third stronger with a pinch, stops particles at CERN, powers every MRI scan, survives rocket exhaust at 2,500 degrees, 80,000 tons a year. One family, no headlines. Next time you drive over a bridge, remember, somewhere in that steel, there are atoms from a hole in the ground in central Brazil. And there's only one hole that matters. Coming up, a liquid metal so dangerous that one broken thermometer can evacuate a building. And they still make thousands of tons of it every year. Picture a liquid that goes through at least 10 different transformations before it ends up in the tank of a truck, tractor, or generator. It's boiled, compressed, broken down into molecules, reassembled, cleaned with hydrogen, and tested dozens of times. All of this so an engine can run for hours under load, in scorching heat and freezing cold, without failures or surprises. Diesel fuel seems ordinary, but it's actually one of the most complex products of modern industry, where behind every gallon stands engineering, temperature, and cold calculation. Diesel fuel doesn't just appear from crude oil, like gasoline from a pump. It's the product of a long, hot, and highly controlled chain of processes, where crude oil is gradually transformed from a dark, heavy liquid into a precisely defined mixture of molecules capable of running reliably in an engine. Everything starts with oil, but then it's literally broken down into components, sorted, cleaned, and reassembled, this time in the right form. Crude oil begins its journey far from the refinery, at oil fields, where it's lifted from the Earth's depths through wells. Along with the oil, water, gas, sand, and small rock particles come to the surface. So right at the extraction site, it's partially settled and the largest impurities are separated out. Once it's out of the ground, the oil hits the road. Most of the time, that means pipelines, continuously pumping millions of tons of liquid across hundreds, even thousands of miles. Where there are no pipes, tankers or rail cars take over. Either way, by the time the oil reaches the refinery, it's still far from ready. Before processing can begin, the crude has to be prepped. It almost always contains water, dissolved salts, and solid particles. Leave those in, and they'll wreck the equipment fast. Salts cause corrosion, water messes with stable heating, and solids wear down pumps and pipes. So the oil gets heated and run through desalting and dehydration units. There, it's mixed with fresh water to wash out the salts, then an electric field forces the water to separate and settle. After that, the crude is much cleaner, and a lot safer for what comes next. The prepared crude oil enters the refinery's main unit, the atmospheric distillation column. This is a tall metal tower, like a multi-story building, with dozens of horizontal trays or packing material inside. The column maintains a constant temperature difference. It's super hot at the bottom, and the higher you go, the cooler it gets. The oil is first heated intensely in furnaces, usually to around 660 degrees Fahrenheit, and then injected into the middle of the column in this hot state. Once inside, the oil starts behaving completely differently than it did in the pipeline. It partially vaporizes, creating a mixture of vapor and liquid. Lighter components with lower boiling points quickly turn to vapor and rise upward. Heavier fractions stay lower or flow all the way down to the bottom. Each level of the column corresponds to its own temperature range, so the vapors condense exactly where they're comfortable. As a result of this process, crude oil is essentially taken apart
where it remains hottest, settle lubricating oils and heavy residues.
Medium ones below, and the heavy residues remain at the very bottom. Everything happens without chemical reactions. The molecules don't break down or change, they simply separate based on physical properties. It's from this point that the real life of crude oil begins as raw material for fuel, lubricants, and dozens of other products, because each fraction obtained will follow its own technological pathway. This is where diesel fraction first appears. It's heavier than gasoline and kerosene, so it condenses lower down, but it's still light enough to be a liquid fuel. This isn't finished diesel fuel yet, just a halfway point, gas oil. It packs a lot of useful energy, but also plenty of sulfur, nitrogen compounds, and unstable molecules that engines hate. The gas oil that comes out of crude distillation is still miles away from the diesel fuel you pump into your tank. It looks similar, sure, but its makeup is dirty by modern standards. It contains sulfur, nitrogen compounds, traces of metals, and unstable hydrocarbon chains that oxidize easily and form carbon deposits. If you fed this stuff straight into an engine, it would quickly destroy the injectors, catalytic converters, and exhaust cleaning systems. That's exactly why gas oil has to go through a hydro-treating stage. At this stage, the fuel gets channeled into special reactors where they create extremely harsh conditions. Temperature there typically hits several hundred degrees, and pressure runs dozens of times higher than atmospheric. Hydrogen gets fed into the gas oil, and this mixture passes through a catalyst bed. The catalyst doesn't get consumed in the process, but it's what forces the chemical reactions to go fast and in the right direction. Without it, purification would either be way too slow or just flat out impossible on an industrial scale. When the gas oil contacts the hydrogen, a series of reactions kicks off. Sulfur-containing compounds break down, and the sulfur converts into hydrogen sulfide, a gas that's easy to separate from the fuel. Nitrogen compounds transform into ammonia, which also gets removed from the stream. At the same time, hydrogen heals unstable molecules. Double bonds get saturated, and fragile structures rearrange into more stable ones. As a result, the fuel becomes chemically calmer, oxidizes less during storage, and behaves better during combustion. After the reactor, the gas oil is cooled and sent to separation units. There, gaseous products, hydrogen sulfide, ammonia, excess hydrogen, are separated from the liquid fuel. Hydrogen is usually recycled back into the process, while harmful gases are sent for further processing or neutralization. It's thanks to this stage that sulfur content in diesel fuel drops by tens or even hundreds of times, down to levels that meet modern environmental standards. The importance of hydrotreatment can't be overstated. It doesn't just cut harmful emissions, it directly impacts engine life. Cleaner fuel puts less wear on fuel injection systems, doesn't poison catalytic converters and particulate filters, burns more consistently, and keeps the engine running predictably. This is really the stage where gas oil stops being a semi-raw material and starts becoming actual diesel fuel suitable for 21st century machinery. But the process doesn't end there. Some diesel components don't even come from primary distillation. Heavy petroleum residues go through vacuum distillation, where reduced pressure extracts even more useful fractions. And if that's still not enough, cracking enters the picture. A process where large, lazy molecules are literally broken down into smaller ones. Hydrocracking is especially critical for diesel because it produces fuel with better combustion characteristics, a higher cetane number, and fewer impurities. After all these stages, different diesel components get blended together. This isn't some random pouring from one barrel to another. It's precise recipe-based mixing. Engineers dial in the proportions so the fuel meets standards. Good ignition, no thickening in the cold, minimal smoke, and no damage to the fuel system. At this stage, they add additives, tiny amounts, but with big impact. They improve lubrication properties, protect against corrosion, reduce foaming, and help the engine start up in winter. Seasonality is a whole different story. Summer diesel is thicker and more stable in warm temperatures. Winter diesel undergoes additional processing. Components that could crystallize in the cold are removed or modified. Otherwise, at 14 degrees Fahrenheit, the fuel starts turning into a cloudy sludge that clogs the filters. For extremely cold regions, they make Arctic diesel, lighter, pricier, and way more complex to produce. Once the fuel's ready, it's stored in tanks, then shipped to fuel depots, and finally to gas stations. But even along that route, it can still be tested, filtered, and adjusted. Diesel isn't a product where you can afford close enough. One small mistake at the refinery can turn into widespread equipment failures. Every second globally, over 3 billion gigabytes of data are transmitted. But did you know that all this happens thanks to a thread thinner than a human hair? And that this thread starts with ordinary sand. Not beach sand, but perfectly pure quartz, where there's only one impurity per million parts. To create fiber optic cable that transmits light at a speed exceeding 300,000 kilometers per second, you have to go through a journey involving chemical vapors, sterile laboratories, a 2,500-degree furnace, and lasers that monitor every microcrack. This process looks more like manufacturing a spaceship than a cable, but it is the foundation of the internet you are using right now. To create a thread capable of transmitting light at a speed exceeding 186,000 miles per second, you have to start with sand. But not just any sand, only special, extremely pure quartz sand, where the main substance is silicon dioxide. For fiber optic production, sand with a silica content of over 99.9% is used, meaning in 1 million parts, there's only 1 part of impurities. Imagine this. In every pound of raw material, no more than a few millionths of an ounce of impurities. And this is critical, because even 1 billionth of an inch of foreign metal or organic matter can cause light scattering or absorption in the fiber optic cable. And then the signal, which was supposed to travel 60 miles without amplification, simply disappears. Raw material for fiber optic cable isn't just washed or filtered, it's purified at the molecular level. Manufacturers often use vapor phase chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and deposited as pure vapor. And only then is it converted back into glass. Add to this strict control of temperature, humidity, air currents in clean rooms, and you'll get an idea of how far this is from an ordinary sandy beach. Production laboratories look more like National Aeronautics and Space Administration sterile zones than a glass workshop. And all for the sake of ensuring there's not a single defect in every yard of the future fiber. Because when you're transmitting light over thousands of miles, even one microscratch can cost you signal quality. A large transparent glass cylinder that will later be melted and drawn into a very thin thread. This is the fiber optic preform. This huge glass rod is made using a method called vapor deposition. In a large furnace, air is mixed with very pure gases. These are different substances that turn into vapor when heated. These vapors hit the inner surface of a transparent tube, which is heated very intensely. When the vapors touch the hot wall of the tube, they deposit and turn into tiny droplets of glass, like dew collecting on leaves in the morning. Gradually, these droplets collect, layer by layer, until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it collapses into a dense, solid rod. And this is our preform. The preform is placed in a special furnace that heats up very intensely. The temperature inside it reaches approximately 4,700 degrees Fahrenheit. This temperature is so high that the glass becomes soft and starts to melt, like caramel on a stove. When the end of the preform melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and a thin thread is formed from it. This thread, the optical fiber, is drawn at a speed of approximately 1,000 feet per minute. Imagine that. It's faster than a cyclist moving through the city. It's important for the thread to be of uniform thickness throughout its length. The thickness of an optical fiber is usually around 125 microns, or approximately 0.005 inches. That's very, very thin. For comparison, the average human hair is about 100 microns thick or less. To keep this diameter under control, special instruments are used during the process. They look at the thread in real time and measure its thickness. If the thread starts to become thicker or thinner, the system automatically changes the drawing speed or the furnace temperature to correct it. After the optical fiber has been drawn from the preform and has become a thin, transparent thread, it needs to be protected. The fiber is very thin and fragile. If left unprotected, it can easily break, cracks will appear, or dirt will get on it. Therefore, immediately after drawing, the fiber is coated with a special protective layer. A thin thread is pulled from the furnace. After the furnace, the thread immediately goes into a coating machine. This is a special device that clothes the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. It's like a small tube or nozzle, inside which there's molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly applied to it. The polymer has very low viscosity, so that the coating is thin and even, but dense enough to protect the fiber. This coating layer usually consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks and allows the fiber to bend. The secondary coating is harder and more rigid, protecting against external influences, dust, and scratches. These two layers are applied sequentially, one after the other, to provide reliable protection. After applying the liquid coating, the coated fiber passes through special forming rollers. They regulate the thickness and evenness of the layer, pressing the coating uniformly along the entire length of the fiber. These rollers are very precisely calibrated so that the layer is not too thick or thin. After the polymer has been applied and shaped, the fiber passes through a zone of ultraviolet light. Here, the polymer instantly hardens under the influence of ultraviolet lamps. This is a process called polymerization. Anyone who gets their nails done knows how this happens. Ultraviolet lamps emit light of a specific wavelength that activates chemical reactions in the polymer. Thanks to this, the coating quickly becomes solid, while retaining its elasticity and ability to protect the fiber. This is a very fast process. The coating solidifies in fractions of a second, literally. This method does not heat the fiber, so it doesn't damage it. This provides very strong and durable protection. The entire machine is equipped with sensors and control systems. They constantly measure the coating thickness, fiber feed speed, and uniformity of application. If the coating layer is too thin or there are defects, the system either stops the process or adjusts the parameters to avoid defects. At the end of all this technological magic, a spooling module, rotating with a hum resembling the sound of a jet engine, only in miniature. The fiber, like transparent silk, lies down smoothly and precisely, coil after coil. It shimmers in the light of the lamps, reflecting cold blue and white hues. The spool moves smoothly, to the left, then to the right, with millimeter precision, as if an artist is painting pictures with movement. One wrong angle, and everything will go haywire. So the system automatically adjusts the rotation speed and fiber tension with surgical precision. Around are sensors, lasers, cameras. They carefully ensure that the fiber lies flat, doesn't twist, and doesn't create tension. With every minute, more and more layers appear on the spool. Imagine, in a few hours, there are already several feet of thin, almost invisible fiber there. And all this, without a single break, without a single scratch. Because even a micro crack, and the light signal will get messed up, like a radio wave in a storm. Before cable assembly begins, the fiber from the spool is carefully wound onto a production line. Since one cable usually contains several fibers, individual threads are combined into ribbons or modules. For ribbons, the fibers are arranged parallel in a single plane, for example, 12 pieces, and glued together with a special resin. This makes them easier to work with during connection. For bundles, the fibers are twisted into a spiral strand and placed in a plastic tube. These ribbons or bundles are then placed into buffer tubes, thin, flexible plastic channels that provide space for the fiber's slight movements. This is important because when the cable's temperature changes or it's bent, the fiber slightly expands or contracts, and the buffer tube helps prevent it from being damaged. A gel that repels water and absorbs vibrations can also be added inside these tubes. Around the buffer tubes, strengthening elements are added. Fiberglass or Kevlar, very strong threads that protect the cable from stretching. Metal wire, for additional mechanical strength or grounding. A central strength member, a rigid element in the center that maintains the cable's shape. These reinforcements are needed so the cable can withstand tension, impacts, bending, and remain intact for decades. All of this is wrapped in an outer jacket. This is a dense plastic or polyethylene pipe resistant to ultraviolet light, moisture, rodents, temperature fluctuations. The cable is tested. The bandwidth of each fiber is checked, as is its bending strength and resistance to moisture. Then it's wound onto large drums, marked, and technical documents are added, and it's ready for transportation and installation. This metal tank, the size of a 10-story building, holds temperatures of -300 degrees. For it to carry rocket fuel or liquefied gas, there's no room for a single mistake in those walls. One microscopic air bubble in a welding seam, and the entire tank, weighing 150,000 pounds, becomes scrap. No fixing it after. No second chance. That's why every inch of that seam gets checked with X-rays, ultrasound, and helium. The gas with the smallest atoms in nature, finding microcracks where water wouldn't even seep through. And there's one moment in this process that makes the entire factory hold its breath. Today, I'm showing you inside. It all starts with choosing the metal, and this is the first stage where everything gets really expensive. Regular steel won't cut it here. It'll just die from the cold. We use special aluminum alloys or nickel-rich stainless steel. These metal sheets are 3/4 of an inch thick, sometimes over 2 inches if the internal pressure is going to be seriously high. For example, manufacturing tanks for liquid hydrogen demand such metal purity that it's X-rayed before it even hits the welding table. Every sheet is marked and tracked, because if there's a void or impurity hiding somewhere in the structure, it'll become a rupture point under the cold. This is the foundation that holds all cryogenic equipment safety together. The welding process is a whole other story that makes a lot of engineers go gray prematurely. You can't just grab an electrode and weld 2 pieces of metal together. We use automated plasma or argon welding under a layer of special flux. The weld has to be stronger than the metal itself. Every inch of that weld goes through 3 stages of inspection. First, there's visual examination, then ultrasound, and finally, full X-ray scanning. We're looking for pores the size of dust particles. If even one air bubble is found in the weld, that entire massive tank gets sent to the scrap heap. There's zero allowance for fixing mistakes by welding over the top. That's the answer to how you ensure hermetic sealing and safety for decades ahead. Now we're getting to the coolest design feature. A cryogenic tank is actually 2 vessels, one inside the other. It's like a Russian nesting doll, where there's a gap 6 to 12 inches wide between the outer and inner shell. The inner tank holds the actual fuel, and the outer one protects it from the environment. But the real secret isn't the double walls, it's what's between them. There has to be absolute emptiness. We create a vacuum so deep that almost no air molecules remain. This prevents heat from transferring from the warm outer shell to the super cold inner one. Without this vacuum, liquid oxygen at -297 degrees Fahrenheit would boil faster than water in a kettle. To make this thermal barrier even more effective, we use what's called multi-layer insulation. Workers manually wrap the inner tank with dozens of layers of special foil and fiberglass. It looks like we're preparing a giant baked potato for giants. Each layer acts like a mirror, reflecting thermal radiation back into space. In other cases, we fill the gap between the walls with perlite, a volcanic sand we puff up into light white beads. It takes thousands of pounds to fill all the voids. Vacuum insulation testing takes weeks. Powerful pumps run day and night, sucking out air until sensors show the required level of vacuum. It's tedious, but a critical stage, because the vacuum is the only thing standing between calm gas storage and a massive explosion. The scale of these structures is mind-blowing. Some liquefied natural gas storage tanks stand over 100 feet tall and can hold millions of gallons of fuel. The weight of such an empty tank can reach 150,000 pounds. When it's filled, the load on the foundation becomes colossal. This isn't just a barrel on legs. It's a complex engineered structure with its own system of valves, sensors, and evaporators. All of this has to work in conditions where ambient temperature can swing from -30 to +110 degrees Fahrenheit, while inside, eternal winter reigns. The space industry is the main customer for these technologies. A rocket needs liquid oxygen and hydrogen to break free from gravity's grip. If a tank at the launch site springs a leak, a launch worth hundreds of millions of dollars gets scrubbed. But cryogenics aren't just for flights to Mars. Energy and industry consume these technologies in massive quantities. The whole world is now shifting to liquefied natural gas, and you can't transport or store it without these steel thermoses. Medicine, where liquid nitrogen is used to store biological materials at -320 degrees Fahrenheit, also depends completely on the quality of these welds. The most nerve-wracking moment at the factory? The helium leak test. Helium is a gas with incredibly tiny atoms that can slip through any microscopic crack where even water or air would get stuck. We pump helium into the inner tank at 500 pounds per square inch and scan the outer surface with special detectors. Sniffers. It's like finding a needle in a haystack, except if we find the needle, we have to explain to the customer why delivery just got pushed back a month. Nobody smiles here until the instrument shows absolutely zero leakage. This is the final exam for the entire factory crew. If you've ever wondered how cryogenic tanks work, here's the deal. They run on pressure differential. When we draw gas from the tank, a small portion of the liquid converts to vapor, maintaining constant pressure inside. It's a self-regulating system, but it demands perfectly calibrated hardware. All those valves and pipes are also made from special alloys and put through cold testing. We freeze them in liquid nitrogen baths to make sure they won't seize up at the worst possible moment. Another thing that blows your mind: how these giants get transported. When a tank 80 feet long rolls out of the factory gates, it becomes a full-on military operation. Special platforms with dozens of wheels slowly haul it to its destination. We have to be absolutely certain that during all that bumping on the road, the inner tank doesn't rip away from its supports. Those supports, by the way, aren't made of metal. They're made of special composite plastic, because metal conducts heat way too well. It's another tiny detail that shows just how complex the manufacturing really is. Right now there's a lot of talk about the hydrogen economy, and that means demand for these tanks is going to explode thousands of times over. But the number of facilities that can maintain these quality standards remains incredibly small. This isn't production you can scale up overnight. It takes years to train a welder to work with these alloys, and even longer to dial in the vacuum systems. This is a world where we're playing very dangerous games with physics, and so far, we're winning. I hope you found it fascinating to look at these steel giants and understand why they cost as much as a small fleet of luxury cars. This is where the ability to use our planet's most energy-efficient fuel is born. We walked through the workshops, witnessed plasma welds, and felt the chill of future vacuum. It's been a wild journey into a world where -300 degrees is just a normal working temperature. Thanks for joining me on this tour. Hit that like button if you were blown away by the idea of holding a vacuum inside a tank the size of a house. Subscribe to the channel, because we've got plenty more factories ahead where they create things most people don't even know exist. We'll show you a world made of steel, fire, and incredibly precise calculations. See you in the next review, where we'll be hunting for engineering truth once again in the roar of working machinery. Take care, and keep your pressure in check. Your smartphone weighs 5 pounds and holds a charge for 30 minutes. Your laptop's chained to the wall because the battery dies in 20 minutes. Electric cars don't exist. The battery would weigh more than the entire car and only go 50 miles. Cordless power tools, wireless headphones, anything portable, just impossible. All because we never figured out how to mine and refine one soft, silvery metal that stores more energy per pound than any other practical battery chemistry. Without this metal, we'd still be stuck with 70s technology. Nickel-cadmium batteries that weigh 10 times more, last 10 times less, and leak toxic heavy metals. Your phone would need a brick-sized battery. Today, we're going inside a facility in Nevada, where this metal is extracted from ancient underground brine. And I'll show you what properties make it irreplaceable and what the world looks like if we have to use something else. The Albemarle lithium facility at Silver Peak, Nevada, sits in a desert valley 190 miles northwest of Las Vegas and has been producing lithium continuously since 1966. 10,000 feet beneath the surface lies a massive geothermal brine reservoir containing dissolved lithium chloride that's been concentrating for millions of years. The facility pumps this brine and processes 6,000 tons of lithium carbonate annually. If lithium had never been discovered, all batteries would use nickel-cadmium or lead-acid chemistry. A lithium-ion battery stores 160 watt-hours per kilogram. Nickel-cadmium stores 40. Lead-acid just 30. To match a modern iPhone battery, you'd need 2.5 pounds of nickel-cadmium instead of 2 ounces. The phone becomes a brick. Mobile computing doesn't exist. The first stage pumps geothermal brine from wells drilled 10,000 feet deep. This brine comes up at 200 degrees Fahrenheit, carrying 300 parts per million of dissolved lithium, along with sodium, potassium, and magnesium. The brine flows into massive evaporation ponds, covering thousands of acres, where the Nevada sun and desert wind do the work. Over 12 to 18 months, the water evaporates, and lithium concentration increases from 300 to 6,000 parts per million. This creates lithium's first critical property, extreme reactivity, makes it the lightest metal that can store electrical charge. Lithium atoms give up electrons more easily than any other practical metal, exactly what you need in a battery anode. Without this, you'd need heavier metals like nickel or cadmium, which means heavier batteries for the same energy. After evaporation, the concentrated brine moves to a chemical plant where it's treated with sodium carbonate to precipitate lithium carbonate as a white powder. This powder is washed, filtered, and dried to 99.5% purity. Lithium carbonate looks like fine white sand, ready to ship to battery manufacturers. Lithium's voltage characteristics become critical here. A lithium-ion cell operates at 3.7 volts. Nickel-cadmium runs at 1.2 volts. To match lithium's voltage, you'd need 3 times as many nickel-cadmium cells wired in series, tripling the weight and complexity. A 6-cell lithium laptop battery would require 18 nickel-cadmium cells. A 1-pound battery pack would weigh 7 pounds, making laptops impossible to carry. Lithium carbonate gets shipped to battery manufacturers, where it's processed into lithium metal or lithium compounds for battery cathodes and anodes. Modern lithium-ion batteries use lithium cobalt oxide or lithium iron phosphate for the cathode and graphite with embedded lithium for the anode. During charging, lithium ions move from the cathode to the anode through the electrolyte. During discharge, they move back, generating current. This reversible movement creates unmatched energy density. A lithium-ion battery handles 1,000 cycles while retaining 80% capacity. Nickel-cadmium manages 500 cycles. Lead-acid gets 300. Without lithium, devices need battery replacement twice as often, generating toxic waste because nickel-cadmium contains poisonous cadmium and lead-acid contains brain-damaging lead. Battery manufacturers shape lithium electrodes into thin sheets and stack them with separators, creating battery cells. Multiple cells connect to form packs for phones, laptops, cars, and tools. Each application demands specific energy density and safety features, but all depend on lithium's unique properties. Lithium's power-to-weight ratio is revolutionary. The Tesla Model 3 has a battery pack weighing 1,000 pounds that stores 75 kilowatt-hours, delivering 300 miles of range. With nickel-cadmium, you'd need 6,000 pounds of batteries to match that energy, but the car weighs only 3,500 pounds total. The battery weighs more than the car. You can't build a practical electric vehicle. Tesla doesn't exist. Electric cars remain a failed experiment from the early 1900s. Every batch of lithium and every battery goes through rigorous safety testing, and there's a specific reason why lithium battery safety standards are so incredibly strict. In 2016, Samsung released the Galaxy Note 7 smartphone with a lithium-ion battery that had a design flaw. The internal structure allowed the positive and negative electrodes to touch under certain conditions, creating a short circuit. Samsung had to recall 2.5 million phones globally. The recall cost them $5.3 billion. Airlines banned the Note 7 on flights. The incident nearly destroyed Samsung's phone business and proved that lithium batteries demand perfect manufacturing with zero tolerance for defects. Today, every lithium battery undergoes crush testing, puncture testing, thermal cycling between -40 and 150 degrees Fahrenheit, overcharging, and internal short-circuit simulation. The rejection rate for lithium battery cells is around 8%. Lithium that's passed all testing gets shipped to electronics manufacturers around the world. The Silver Peak facility produces 6,000 tons annually, but global production is roughly 400,000 tons because demand is massive. Without lithium, portable electronics barely exist. Your phone stays plugged into the wall, like it's the 80s. Laptops are 20-pound luggables with 30-minute battery life. Wireless earbuds, cordless drills, e-bikes, drones, portable medical devices, none of it exists. Anything portable and electronic requires a gas generator or an extension cord. Electric vehicles are impossible. Every automaker tried EVs with lead-acid or nickel metal hydride batteries in the 90s and 2000s. All failed. Maximum range 60 to 80 miles. Batteries died after 2 years. Without lithium-ion, Tesla never gets started. EVs remain a failed technology, and we're stuck with gas cars with no viable alternative. Renewable energy storage doesn't work at practical scale. Solar and wind need massive batteries to store energy when the sun doesn't shine or the wind doesn't blow. Without lithium, these systems would be warehouses full of lead-acid batteries weighing 50 times more, costing 10 times more, needing replacement every 3 years. Grid-scale energy storage is economically impossible. Renewable energy remains tiny because it's too unreliable without storage. Without this lightweight, high-voltage metal, we're stuck in a world where electronics stay plugged into outlets, portable devices don't exist, electric cars are impossible, and renewable energy can't replace fossil fuels. You've seen how brine containing 300 parts per million lithium concentrates through evaporation to 6,000 parts per million. How chemical processing creates 99.5% pure lithium carbonate. How lithium's properties create batteries with 4 times the energy density of alternatives. And why the Galaxy Note 7 proved that lithium production demands absolute precision. If this hooked you, subscribe for more content making modern life possible. Thanks for watching. Every year, humanity produces over 4 billion tons of concrete, more than any other material on the planet. It's what our cities, bridges, and roads are built from. But every crack is like a tiny timer ticking toward destruction, started the moment water seeps inside. Now imagine concrete that actually lives, breathes, and heals itself. No people, no repairs. Deep in labs across the Netherlands, USA, and Japan, a game-changing material is being born. Inside it, bacteria or microcapsules that can seal cracks on their own, just like skin healing after a wound. How is this even possible? How did a lifeless material gain the ability to regenerate? Stick around until the end, and you'll find out how scientists brought concrete to life. Self-healing concrete. Sounds like something out of a sci-fi movie, but it's already here. Scientists invented it to solve one of construction's biggest headaches: cracks. Regular concrete starts drying out and cracking over time from temperature swings, moisture, or just plain stress. And a crack isn't just a scratch. Water gets inside, the rebar starts rusting, the structure weakens, and eventually, you're looking at expensive repairs or even a collapse. That's why researchers decided to create concrete that can patch itself up, no human help required. Sounds crazy, but it's actually pretty logical. There are 2 main technologies that make this possible: microbiological and mineral. The first one uses real living organisms. So-called bioconcrete was developed by Dutch researchers, and the principle is pretty straightforward. They add special bacteria to regular concrete mix, usually Bacillus pseudofermis or Bacillus conii. These bacteria can stay dormant for years, like seeds in dry soil. Along with the bacteria, they add nutrients, usually calcium lactate. And while the concrete stays intact, the bacteria just sleep. But when a crack forms and moisture gets in, they wake up. That's when the real microscopic work begins. The bacteria start consuming the nutrient substrate and, through their life processes, produce calcium carbonate, basically the same mineral that makes up seashells and limestone. That's what seals the crack from the inside, like the concrete is fixing itself. The results are impressive. Micro cracks up to 0.03 of an inch can disappear completely within a few weeks. And all without human intervention, purely thanks to nature that's been built into an artificial material. The second technology is less alive, but no less impressive. Instead of bacteria, it uses chemistry. Tiny capsules are added to the concrete, containing an active substance inside. For example, epoxy resin or sodium silicate. These grain-sized capsules are evenly distributed throughout the mix. When the concrete cracks, some of the capsules burst too. The substance inside comes out, fills the crack, and hardens on contact with air or moisture. The result is the material literally heals itself. It's similar to how certain car paints can heal scratches with heat, except this process is way more complex and large-scale. The advantage of this approach is that it works even in dry conditions, where bacteria might not activate. The downside is cost. Creating the capsules is more complex, so this concrete is pricier. But when you calculate the cost of repairing bridges or tunnels, it becomes clear. The payoff is huge. Interestingly, these technologies don't cancel each other out. Some companies are experimenting with combining biological and chemical methods to create concrete that could self-heal under any conditions. Underwater, in the desert, or in freezing cold. Testing shows that structures made with this concrete last 2 to 3 times longer than regular ones. Bridges, roads, dams, parking garages, all of this can be made nearly eternal. For example, the Netherlands already built a lakeside lifeguard station using bioconcrete, and after several years, it hasn't needed any repairs. The idea is spreading fast around the world. In the US, these materials are being tested in bridges, in the UK, in sidewalk paving, and in Japan, even in concrete for coastal reinforcements that have to withstand salt water. Regular concrete, even the highest quality, has a shelf life, roughly 50 years. After that, cracks start appearing, water penetrates inside, rebar rusts, and the structure gradually weakens. Self-healing concrete changes these rules. Thanks to bacteria or microcapsules, it can heal microdamage before it becomes a problem. That's why the service life of structures can nearly double, from 100 to 120 years. That means one bridge or building can stand for 2 human generations without major repairs. Sure, this material isn't cheap yet. It costs several times more than regular concrete, on average 3 to 5 times more. But if you look at the long game, it's totally worth it. Maintaining, repairing, and restoring structures costs governments and companies millions of dollars every year. Self-healing concrete cuts those costs to a minimum. Basically, it's like buying a car that changes its own oil and fixes its own brakes. Expensive upfront, but then smooth sailing and economical. The Netherlands became the real home of self-healing concrete. Right here, at Delft University of Technology, the idea emerged to add living bacteria to the mix that could repair concrete from the inside. The man behind this idea is Dutch microbiologist and engineer Hendrik Jonkers. Nature inspired him. He noticed that certain bacteria can survive in limestone rock and create mineral deposits, filling micro cracks in stone. That's when Jonkers asked himself, if nature can heal stone, why not make concrete that does the same? In the early 2000s, he started experiments with different bacterial strains, looking for ones that could withstand concrete's alkaline environment and stay viable for years. After numerous trials, the best candidates turned out to be Bacillus pseudofirmis and Bacillus conii, spores that can sleep for decades and activate only when moisture appears. Jonkers added them to concrete along with a food source, calcium lactate. The results were mind-blowing. When the concrete cracked, the bacteria woke up and produced calcium carbonate, which sealed the cracks like natural glue. Jonkers called his invention bioconcrete, and soon the whole world was talking about it. Later, Delft University launched a project to test bioconcrete under real-world conditions. In 2015, the Netherlands built the first lakeside structure using this material. Years later, it remained in excellent condition without any repairs. Now Jonkers' lab is working with construction companies and governments from other countries, perfecting the formula to make it cheaper and more accessible. The USA and UK bet on the mineral technology for self-healing concrete, which doesn't require living organisms, but works through special microcapsules with healing substances inside. These countries are actively investing in research on materials that can automatically restore minor damage without human involvement. The principle is pretty simple, but looks impressive. Capsules or microcapsules filled with special gel, epoxy resin, or sodium silicate are added to the concrete mix. When the concrete surface stays intact, the capsules preserve their contents without reacting with the environment. But as soon as a crack appears, the capsule ruptures and the liquid flows into the damaged zone. On contact with moisture or oxygen, the substance hardens, gluing the crack edges together and returning the structure's original strength. These systems are currently being tested in US Army labs and British research centres, including Cambridge University. In the UK, they're even building experimental road and bridge sections with this material to track how it behaves under rain, vibrations, and temperature swings. American experts went even further. They're experimenting with capsules that can activate multiple times. Inside these capsules are microgels that not only fill cracks, but also expand on contact with water, creating a hermetic barrier against corrosion. This is especially crucial for bridges and skyscrapers in coastal cities, where concrete constantly faces moisture and salts. Test results show that cracks up to a few hundredths of an inch wide can seal themselves in less than a week. And if the damage is larger, the process takes longer, but still happens without human involvement. Such technologies can significantly extend the service life of roads, tunnels, and even military structures, which is especially valuable under extreme loads. Every year, the world mines millions of ounces of a metal most people never even think about. But without it, modern civilization would literally grind to a halt. What if I told you there's a metal hiding in every car that can absorb hydrogen hundreds of times its own volume, operate at temperatures over 5,000 degrees Fahrenheit, and cost more than gold? Palladium seems invisible, but it's what cleans the exhaust from millions of vehicles, drives key chemical reactions, and determines the price of entire industries. Where does it come from? Why is there so little of it? And what hidden detail at the end of this video will change how you think about this metal forever? Stick around to find out. Palladium is a chemical element from the platinum metals group that combines rarity, high chemical stability, and exceptional physical properties. In the periodic table, it has atomic number 46 and a silvery white color that persists even after prolonged exposure to air. At a density of around 7 pounds per cubic inch, it's lighter than platinum, yet strong enough to withstand significant mechanical stress. Palladium's melting point sits at approximately 2,830 degrees Fahrenheit, and it boils at temperatures exceeding 5,400 degrees Fahrenheit, making it suitable for high thermal load applications. One of palladium's most fascinating features is its ability to absorb hydrogen in amounts hundreds of times greater than its own volume. At room temperature, the metal literally pulls hydrogen atoms into its crystal lattice, forming solid solutions. This property is actively used in hydrogen purification technologies, membrane systems, and alternative energy research. Palladium maintains its stability and doesn't crumble, which sets it apart from many other metals. The industrial importance of palladium is enormous. The bulk of global consumption goes into catalytic converters for automotive exhaust systems. In these devices, palladium accelerates the oxidation of carbon monoxide and unburned hydrocarbons, converting them into less harmful compounds. A single passenger car might use only a few hundredths of an ounce of the metal, but with millions of vehicles in play, total demand hits tens of thousands of pounds per year. It's this industry that makes the palladium market incredibly sensitive to shifts in global auto production and environmental regulations. Beyond the automotive world, palladium is everywhere in electronics. It shows up in multi-layer ceramic capacitors, contact assemblies, connectors, and microchips. Thin palladium coatings shield components from corrosion and wear, maintaining stable conductivity even after thousands of power cycles. In electronic components, the metal's mass is usually measured in fractions of an ounce, or even grains, but collectively these amounts carry serious economic weight. Jewelry wouldn't be the same without palladium. It's added to gold alloys to create white gold without using nickel, crucial for people with sensitive skin. Pure palladium is used to make rings, earrings, and watches because it's lighter than platinum and more comfortable to wear. Palladium pieces hold their shape, don't tarnish, and rarely need polishing. Geologically speaking, palladium is pretty rare. Its average concentration in Earth's crust is just a few millionths of a percent. Major deposits are tied to magmatic complexes and sulfide ores, where palladium occurs alongside platinum group metals, nickel and copper. Mining often takes place at great depths, sometimes several thousand feet below the surface, which makes the process significantly more complex and expensive. Because of this, the price of palladium can fluctuate sharply depending on the political stability of mining regions and the state of the global economy. The chemical behavior of palladium makes it valuable in laboratory practice. It's one of the key catalysts in organic synthesis reactions, particularly in carbon-carbon bond formation processes. Thanks to this, palladium plays an important role in the production of pharmaceuticals, agrochemicals, and specialty polymers. Even microscopic amounts of the metal, measured in milligrams or grains, can substantially impact the speed and selectivity of reactions. Palladium's physical properties are equally noteworthy. It responds well to cold working, rolls easily into thin sheets, and draws into wire. From a single ounce ingot, you can produce a sheet covering several square feet. At the same time, the metal maintains high electrical and thermal conductivity, making it useful in specialized technical applications. Palladium is almost never mined by itself. It's a byproduct of nickel, copper, and platinum metal extraction. Everything starts in underground or open pit mines, where sulfide ore is pulled from depths of hundreds or thousands of feet. The ore is crushed and ground into a fine powder, then mixed with water and reagents and subjected to flotation. The result is a concentrate enriched with copper and nickel sulfides and traces of palladium. Next, the concentrate gets roasted in furnaces at temperatures exceeding 1600 degrees Fahrenheit, stripping away sulfur and organic residues. The resulting material is melted, separating into a metallic phase and slag. At this stage, palladium is still mixed with other platinum group metals. Separation begins at refineries, where alloys are dissolved in acids and subjected to multi-stage chemical purification. Platinum, rhodium, and iridium are precipitated sequentially, while palladium is isolated as salts, which are then reduced to metal. The final stage of palladium extraction begins when, after a long chain of chemical purification, the metal has been separated from other platinum elements and exists as salts or spongy precipitate. This material is thoroughly rinsed with distilled water to remove traces of acids and impurities, then dried in furnaces at temperatures of several hundred degrees Fahrenheit. It looks like a gray-black powder with very low bulk density, which doesn't yet have the properties of compact metal. Next, the powder or palladium sponge is fed into melting facilities. Most commonly, induction or electric arc furnaces are used, where the metal is heated in crucibles made from inert materials. The atmosphere inside the furnace is monitored especially carefully. Argon is introduced, or the space is evacuated to prevent oxidation and losses. The temperature is gradually raised above 2,800 degrees Fahrenheit, until the palladium particles fuse into a uniform molten mass with a mirror-like surface. When the metal is fully molten, it's held in the furnace for a set period to even out the composition. Even traces of other metals are measured here in fractions of an ounce per ton, so samples can be pulled directly from the melt for lab analysis. If purity doesn't hit the target level, the melt goes back for additional refining. Only after confirming readings above 99.9% is the palladium cleared for forming. To produce ingots, the liquid metal is carefully poured into preheated graphite or steel molds. The weight of these ingots can range from a few ounces to tens of pounds, depending on customer needs. Cooling happens under controlled conditions to avoid internal stress and cracks. After solidification, the ingots are removed, weighed, marked, and the chemical composition is checked one more time. If palladium is destined for catalysts or the chemical industry, it might skip the ingot stage entirely and be turned straight into powder. To do this, the metal is dissolved again, then reduced under controlled conditions to produce particles of a specific size. This powder gets packed into airtight containers, where every single gram carries serious value. Global palladium production is typically measured in the hundreds of thousands of troy ounces per year. On average, worldwide output hovers around 6 to 7 million ounces annually, with more than 2/3 of that volume coming from just 2 countries. Another key figure, secondary recycling, mostly from used automotive catalytic converters, accounts for 25 to 30% of global supply. By comparison, for many other precious metals, the recycling share is significantly lower. In your average ore, the palladium content is incredibly tiny. We're talking a few hundredths of an ounce per short ton of rock, sometimes even less. That means to get just 1 pound of pure metal, you need to process thousands of tons of ore. That's exactly why production costs are so sensitive to energy expenses and logistics. Every year, millions of tons of metal waste get recycled worldwide, but only at the very end of this massive process does a substance emerge that's heavier than almost anything you've ever held in your hands. Picture a metal where a tiny piece weighs as much as a brick, and extracting it is more like hunting ghosts through fire and acid. Today, we're stepping inside a facility where one of the rarest and most mysterious metals on the planet is born from dirty sludge: osmium. But the most shocking part isn't its weight. It's what you have to go through to get even 1 small bar. And trust me, if you stick around until the end of this video, you'll learn a fact about this metal that literally breaks logic and makes you question the laws of physics. We're now entering the primary processing facility for platinum sludges. Everything around here is humming, steam's bursting out from under valves, and the workers look like they're gearing up for a flight to another galaxy based on the sheer amount of protective gear they're wearing. And that's no surprise. Osmium is basically the heavyweight champion of the periodic table, and it doesn't tolerate amateurs. It's twice as dense as lead. Just think about that for a second. If you grab a cube of this metal with sides only 4 inches long, it'll weigh nearly 22 pounds. That's like trying to pick up a full-grown cat that's compressed itself down to the size of a matchbox. The process of extracting osmium is a real adventure for anyone who loves complex flowcharts and intellectual challenges. This metal doesn't just lie around in proud nuggets deep in the earth, waiting for some lucky prospector to pick it up and slip it into their pocket. Nope, it's way trickier than that, and hides itself in the residues left over from the industrial purification of copper and nickel. Picture a whole mountain of rock that's already been processed, squeezed for everything possible, and only at the very end, in the dirty sludge, this heavyweight remains. You and I walk past massive vats where all hell breaks loose because the metal mixture gets hit with aggressive chlorine and insanely high temperatures. It looks like a set from a movie about the future, where humanity learned to extract value from dust. The work starts with anode slime. That's the sediment left over after electrolysis. To get to the osmium, specialists have to literally dismantle the molecular structure of this waste. First, the slime gets treated with acids to wash out the more cooperative metals. When it's our hero's turn, thermal processing kicks in. Temperatures here reach thousands of degrees Fahrenheit. This isn't just heating, it's total transformation of matter under the watch of dozens of sensors. When the mixture hits the reactors with chlorine, the most critical stage begins. Osmium reacts and transforms into a volatile compound. This gas needs to be captured with pharmaceutical precision. The slightest error in pressure or temperature, and the precious metal simply flies up the stack, leaving behind nothing but a foul smell. Special absorption towers step by step pull the gas in, converting it into a solution. It's like hunting a ghost, except instead of traps, you're using complex chemical filters. Next, the solution goes through several more purification stages until finally a precipitate appears, pure osmium salt. But that's still not the end of the road. This salt gets roasted again in a stream of hydrogen to produce that same dark blue powder. Every pound of this powder, that's the result of hundreds of workers and massive machines grinding away. Looking at these vats, you realize that osmium extraction isn't just metallurgy. It's the pinnacle of engineering genius, where every move costs thousands of dollars. This is work for the patient and the bold, because this metal doesn't forgive mistakes, but it rewards those who make it through all these fiery and chemical obstacles with its otherworldly strength. To extract it, you need to convert it into osmium tetroxide. And this is where the fun really begins, because this gas smells like someone decided to mix bleach with rotten radish and set it all on fire in a closed room. The metal's name actually comes from the Greek word meaning smell, and trust me, the Greeks knew what they were talking about. We move on to the separation laboratory. Here reigns an atmosphere of sterility that contrasts with the dirty rumble of the previous workshop. Scientists in white coats manipulate glass tubes and retorts. The whole process looks like a very expensive and dangerous cooking show. They extract osmium as a fine, dark blue powder. This powder looks beautiful, but it's incredibly treacherous. If you heat it in open air, it instantly becomes a toxic gas that can ruin not just your day, but your health for years to come. So airtightness is everything here. Look at these furnaces. They operate at temperatures that are hard to fathom, over 5,000 degrees Fahrenheit. That's way hotter than the surface of some stars. Because osmium has an incredibly high melting point, you can't just melt it in a bucket and pour it into molds. They use powder metallurgy methods here. The powder gets pressed under gigantic pressure, then sintered in a vacuum. What you get is like a metal sandwich that then becomes a monolith. It's fascinating to watch them try to cut this metal. Regular saws and drills are useless here. They just dull or snap like they're made of chocolate. Osmium is so hard and brittle at the same time that you can only work with it using lasers or supersonic water jets with added abrasives. It's a real challenge for engineers. Every disc or sphere produced costs a small fortune, because making a single part burns as much energy as a small town uses over a weekend. Why even bother with such a finicky material, you might ask? Well, besides looking like a chunk of frozen blue sky, it's incredibly wear-resistant. It's used where you need something eternal, in high-voltage switch contacts or in the tips of very expensive fountain pens used to sign peace treaties. This is one of those cases where quality justifies every cent spent and every whiff of that weird smell of ozone and chemistry. I'm standing next to a finished ingot. It's small, about the size of my palm. But when I try to move it, my muscles tense up like I'm pushing a small car. This little guy weighs about 35 pounds. You can't capture this feeling through a camera. It violates every law of logic we're used to in everyday life. You expect lightness, and you get a gravitational punch to your arms. Now we're moving into the packaging zone. Even here, everything's serious. Every gram is accounted for. Every ingot has its own certificate and number. This isn't the kind of metal you accidentally forget in your work jacket pocket. Its market price swings so wildly that investors sometimes drink more sedatives than coffee. But demand for this blue shimmer keeps growing because the world's getting more technological, and osmium, it's exactly the ingredient that makes modern electronics reliable. You know what struck me most at this plant? It's the people. They talk about this metal like it's a living creature with a really bad temper, one they've learned to respect and tame just a little. There's no room for rushing here. Every move is calculated to the inch. Every second in the furnace is accounted for. This isn't just manufacturing. It's a battle of human intellect against the physical limits of matter. We're wrapping up our tour at the finished product display. Here you'll find small parts that'll soon ship all over the world. Some will end up in spacecraft, others will become part of medical devices. And every time you hear about something incredibly strong and durable, remember this blue, smelly, and impossibly heavy metal. Hope you enjoyed this walk along the edge of the periodic table. It was tough in every sense of the word. Don't forget, the world around us is way more interesting than it seems at first glance, especially if you peek behind the fence of a big factory. It was fun showing you this metallic extreme. Until next time at new facilities, where we'll definitely find something else that'll make your eyebrows shoot straight up in surprise. Did you enjoy this format? Maybe you'd like me to prepare a detailed script about manufacturing another rare metal, or talk about the logistics of moving these heavy ingots around. Every single second, over 100 tons of new trash gets created around the world. Think about it. While you're watching this video, an entire truckload of waste appears on our planet. Where does it all end up? For years, the answer was simple: China. That's where Europe, America, and Japan shipped millions of tons of used bottles, paper, and scrap metal. But one day, China said, "That's enough." And suddenly, the world faced a garbage meltdown. But here's the mystery. Why would a country that banned importing other people's trash start searching for it just a few years later? Stick around till the end. You'll discover the secret that flipped the global recycling industry upside down. For many, many years, the entire world, especially wealthy countries in Europe, America, and Japan, got comfortable with a very convenient setup. They'd collect their trash, old plastic, paper, scrap metal, and simply ship it off to China. Massive container ships sailed across the oceans, loaded with tons of used soda bottles, old newspapers, and broken toys. China was like the world's global trash can. But not just a can. It was also a massive recycling operation. Chinese factories would take this waste, sort it, process it, and turn it into new products that they'd sell right back around the world. It was incredibly profitable for China. They got cheap raw materials and created jobs. And for other countries, it was perfect. They got rid of their garbage problem for relatively little money. Everybody was happy, right? Well, almost. But then, around 2018, China said, "Enough." Imagine a huge meeting of Chinese officials where the decision rang out: "We're done accepting other people's trash." They called this policy, very characteristically, National Sword. It was like if your neighbor, whose garage you'd been dumping your junk in for years, suddenly said, "That's it, take it all back. My garage is full and I'm sick of this." And that's when real chaos erupted. Countries that had been carelessly shipping their waste to China for years suddenly found themselves with millions of tons of garbage with nowhere to go. Picture this. Warehouses across Europe and America started filling up with mountains of plastic and paper that were supposed to sail to China, but now had no destination. It was a genuine shock to their recycling industry. What were they supposed to do with all this trash? Dump it in the Pacific Ocean? Toss it in deserts like in post-apocalyptic movies? Of course not, but the panic was massive. Some countries started burning waste in incinerators, which isn't great for the environment since it pollutes the air. Others scrambled to find new trash cans in Southeast Asia, Vietnam, Malaysia, Indonesia. But these countries quickly started pushing back too, because they didn't want to become the world's dumping grounds either. But here's where it gets really interesting. While the world frantically searched for somewhere to shove their plastic mountains, China started feeling a strange hunger. A hunger for plastic, a hunger for waste paper, a hunger for scrap metal. Seems impossible, right? A country that generates the most trash in the world suddenly experiencing a shortage of it? It's like a millionaire who suddenly went broke and is now searching for loose change under the couch cushions. The thing is, Chinese industry had gotten hooked on this imported high. Recycling plants, of which there were, to put it mildly, plenty in the Middle Kingdom, had gotten used to working with cheap, abundant, though not always quality, imported waste. Imagine a huge factory that processes tons of plastic bottles from Germany or the US every day. Its conveyor belts ran non-stop. Its workers knew their job. Its owners counted their profits. And suddenly, bam! The tap of imported raw materials got turned off. National Sword didn't just cut off imports. It left this entire massive industry without its usual food supply. Factories stood idle, capacity sat unused, and business owners pulled their hair out. But why couldn't they just switch to their own Chinese garbage? After all, There are billions of tons of it, right? That's where the devil's in the details. The problem isn't the absence of trash altogether, but the absence of quality, sorted, clean raw materials. The problem is that Chinese citizens don't know how to sort trash. Imagine this. People lived for decades, just like we used to, following the principle of everything in one bin, then off to the dump somewhere. That's the easiest way, you gotta admit. No need to think about anything. No need to separate anything. Just toss it and forget it. And this system that formed over generations, this habit that took root deeper than the oldest tree, suddenly turned out to be wrong. The Chinese government, facing these trash mountains growing faster than bamboo after rain, decided, yeah, this has to stop. We're starting to sort. But something went wrong. Sure, in big cities like Shanghai, where millions of people live in tight quarters, they started implementing mandatory waste separation. Imagine, now you don't just throw out trash, you have to divide it into 4, sometimes 5 different categories: wet waste, dry waste, recyclable waste, and hazardous waste. And all this has to be thrown out at strictly defined times, in strictly defined containers. But that's just the tip of the iceberg. First, even what gets sorted often doesn't meet the cleanliness standards required for recycling. Imagine a plastic bottle you tossed in the right container, but it was poorly washed and still had yogurt residue inside. Or a pizza box soaked with grease. Things like this, if there are too many of them, can ruin an entire batch of raw materials, making it unsuitable for recycling. Recycling plants that previously worked with more or less standardized imported plastic that had already gone through initial sorting abroad suddenly faced Chinese reality, a mixture that requires additional, expensive cleaning stages, or simply gets rejected. Second, logistics. Collecting billions of tons of trash is one thing, but collecting it in such a way that it reaches recycling plants as clean, sorted raw materials that can be economically viable to recycle, that's a completely different story. In many areas of China, especially in smaller cities and rural areas, the secondary raw material collection system is still very primitive. There, trash is still collected haphazardly, and sorting often happens right at the dump site, by hand, which hardly guarantees high quality. But there's another interesting angle here. China is a country that's constantly trying to upgrade itself, to become a leader in everything. And with trash recycling, it's the same story. After National Sword, they decided, okay, if we can't import, we'll build the world's best system ourselves. And they started building, modernizing, investing. New, modern, high-tech recycling plants appeared. They're equipped with the latest equipment, capable of processing massive volumes of secondary raw materials. But they need these raw materials. Clean, quality, preferably pre-sorted. And that's where the paradox emerges. There are plants, there's technology, there's the will to recycle, but there's not enough of the right trash. Picture a giant gleaming factory where robots work, but the conveyor belts move sluggishly because trucks haven't brought enough quality plastic. Or they brought it, but it's so contaminated that it has to be sent to the landfill instead of being recycled. It's like building a luxury restaurant with the best chefs, but having a shortage of fresh ingredients. This hunger for trash isn't just an economic problem, it's also a driver for further change. It's forcing China to accelerate reforms in waste management. The government is putting even more pressure on cities to improve their waste separation and sorting systems, educate the public, and implement fines for improper sorting. New logistics chains are being created for efficient collection and transportation of sorted secondary raw materials to recycling plants. Systems based on artificial intelligence and robotics are being developed for more accurate and efficient trash sorting. Imagine sorting robots analyzing every piece of plastic, determining its type and cleanliness. China aims not only to recycle, but also to use recycled materials in its own production, thereby closing the circular economy loop. This means that a system that previously relied on external sources of raw materials now has to completely reorient itself to internal, more finicky sources. And this trash hunger paradoxically pushes China to finally build a truly efficient and environmentally responsible waste management system. It's like a dragon that created a problem for itself just to heroically solve it later. And who knows, maybe in a few years, China will be not only the world's biggest trash producer, but also its biggest and most efficient recycler. That's the tangled but fascinating trash story from the Middle Kingdom. They extract it in mountains where stone is born from flames and pressure capable of crushing anything alive. Its formation takes hundreds of millions of years, and today, people cut it with diamonds at a speed of 20 miles per hour. But what if I told you that this shiny material, used to decorate palaces and statues, was once the bottom of an ancient ocean, and that every slab of marble is a frozen story of life, death, and time? Watch until the end, and you will see how nature creates its own masterpiece, and people try to uncover its secret. Marble is not just a beautiful stone for decoration or sculpture. It is a material that has millions of years of geological transformation behind it. Its journey begins deep underground, where temperature and pressure change ordinary rocks beyond recognition. The basis of most marble is limestone, a sedimentary rock formed mainly from calcite. Limestone is formed at the bottom of ancient seas and oceans from the remains of marine organisms, corals, mollusks, foraminifera. Over millions of years, these fragments settle, compact, and cement together under pressure to form thick layers. When such layers fall into a zone of tectonic processes, where the Earth's crust moves, compresses, or subsides, they sink into deeper layers of the Earth. There, the temperature can exceed 1,200 degrees Fahrenheit, and the pressure reaches 1,000 atmospheres. Under these conditions, metamorphism begins, the process of transforming rocks without complete melting, but with a change in their structure. During metamorphism, the calcite crystals in the limestone begin to recrystallize. The old grains disappear, and instead, new ones grow, larger, tightly fused together. This process gradually transforms the loose sedimentary rock into a solid monolith with a characteristic shine and granular texture. It is this structure that gives marble its famous ability to be polished. The variety of colors and patterns in marble is the result of impurities that got into the limestone during its formation or metamorphism. If there is iron in the rock, the marble acquires reddish or yellow hues. Graphite or organic matter makes it gray or black. Impurities of serpentinite or chlorite add green tones. Quartz, dolomite, and pyrite create veins, the same patterns that make marble seem alive. Marble is not formed instantly. The process can take hundreds of millions of years. In places where tectonic plates collide, for example, in the Himalayas, the Alps, or the Apennine Peninsula, the rocks experience the most intense pressure. That is why such areas have become world centers for marble quarrying. For example, Carrara in Italy, where white marble of extraordinary purity was formed. During metamorphism, degassing also occurs, the release of carbon dioxide that remained in the pores of the limestone. Because of this, the structure of marble becomes almost non-porous. This density makes it durable, but also more brittle with sudden changes in temperature. In some cases, the process of marble formation can be partially reversible. If the temperature is too high, the calcite begins to melt, forming intermediate forms between metamorphic and igneous rocks. Such transitional marbles are found in areas of contact between limestone and magmatic intrusions, for example, near granite massifs. Another interesting feature is the zonation of formation. In nature, it is rare for an entire layer of marble to have the same structure. In different areas, the pressure and temperature are different, so some layers are coarse-grained, others are fine-grained, some have veins, others have a uniform color. This explains why even within a single quarry, marble of a completely different appearance can be extracted. When geologists study deposits, they are looking for precisely those places where the limestone has undergone complete metamorphism, but has not been destroyed by excess heat or deformation. Sometimes these layers lie at a depth of several hundred feet. Sometimes they come right to the surface, as in Tuscany or Greece. The quarrying and processing of marble is no less fascinating a process than its formation. The modern marble industry combines powerful machinery, precise laser technologies, and artisanal craftsmanship that has barely changed since the time of Michelangelo. The first stage is the identification of the deposit. Geologists conduct research on mountain ranges using georadar, laser scanning, and drilling samples. The goal is to find a layer of marble of the required thickness, color, and uniformity. Sometimes the required layer lies almost on the surface, as in Carrara in Italy, or on the island of Paros in Greece. In other cases, it has to be uncovered, removing tens of feet of rock from above. When the site is prepared, the separation of marble blocks begins. Once, this was done with explosives, but now much more precise and safer methods are used. The main tool is diamond wire saws. This is a steel cable on which hundreds of diamond segments are strung. The cable is stretched between two pulleys and rotates at a speed of over 20 miles per hour, gradually cutting the stone like a string cuts cheese. Thanks to a water cooling system, the cut is even and smooth, without cracks. Another method is drilling vertical and horizontal holes in the rock, through which a diamond wire is then threaded. This forms the rectangular contour of the block. When the cuts are connected, a huge piece of marble, usually weighing from 20 to 50 tons, is separated from the mountain massif. It is propped up with hydraulic jacks, steel wedges are inserted, and the block is gradually released, preventing a sudden fall. Next, the blocks are transported from the quarry to processing plants. On the slopes of mountains, powerful tracked loaders and platforms on heavy trailers are often used for this. In mountainous areas where there are no roads, marble is sometimes lowered by special cable systems, a kind of funicular that leads from the quarry to the valley. In the workshops, the blocks are cut into slabs or blanks. For this, gang saws are used, large frame machines with dozens of steel blades, between which an abrasive mixture with water is fed. In modern production, they have been replaced by diamond circular saws or laser cutting machines. The cutting accuracy reaches fractions of a millimeter. After cutting, the surface of the slabs is ground with abrasive stones of different grits, gradually moving from rough grinding to mirror polishing. If the marble is intended for architectural projects, it is further strengthened. A thin layer of resin or fiberglass is applied to the backside. This prevents chipping during transportation and installation. For sculptures, such reinforcement is not done. On the contrary, they look for a stone with a uniform texture without microcracks. Polishing is a separate art. It is performed on large machines where a series of round abrasive discs pass over the surface, gradually giving it a deep shine. To achieve a perfect effect, powders of tin or cerium oxide are used. It is they who reveal the structure of calcite, and the marble begins to play with reflected light. After polishing, the marble slabs are marked and sorted by color, pattern, and quality. Part of it is sent for export, another part to workshops for carving, facing, or manufacturing architectural details. Sculptors work with marble much more delicately. They use hand chisels, hammers, and now, pneumatic tools that allow them to carefully remove the stone layer by layer. Even with modern technologies, the art of marble processing remains semi-artisanal. It requires an eye, a touch, and an understanding of how the rock behaves. At the end, the marble products are coated with protective waxes or silicone impregnations, which enhance the shine and protect the surface from moisture. For interior work, softer compositions are used. For facades, water-repellent, UV-resistant ones. Quarries are usually located in mountainous areas that are difficult to reach. To cut blocks weighing from 20 to 50 tons, expensive equipment is needed. Diamond wires, cranes, hydraulic jacks. At the same time, about 30 or 40% of the quarried stone is suitable for commercial use. The rest is cracked or defective blocks that go to waste or are crushed into crumb. Due to the mass and fragility of the slabs, they are transported on special trailers or containers with cushioning. For imported marble, delivery can account for up to 30% of the final price. What if the most dangerous part of a suspension bridge isn't what you see? Because inside those main cables, which look like solid metal, there's a hidden structure made of tens of thousands of wires, each one vulnerable to destruction, even from a single drop of salty fog. So why doesn't a bridge weighing thousands of tons collapse every single day? And what happens if moisture gets inside the cable where nobody can spot it? Stick around until the end. You'll discover a secret even bridge engineers don't talk about. The classic example, the Golden Gate in San Francisco. It's got two main cables slung over the towers and anchored into massive concrete blocks in the rock. Each cable's diameter? About 37 inches. We're not talking rope here. This is basically a steel column so thick you'd need 2 or 3 people linking arms just to wrap around it. Inside? 27,572 individual wires, compressed into a perfectly round bundle. Unwind all those wires and lay them end to end, you'd get roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. The weight of just one cable? Close to 24,500 tons. That's comparable to a small cruise ship or a few hundred fully loaded semis. Why use so many individual wires instead of one giant solid rod? Here's the thing. Steel works great in tension, but it doesn't handle defects well, especially in large cross-sections. When an element consists of thousands of independent wires, each one can play a little, taking on a bigger share of the load here, a smaller one there. If for some reason a single wire corrodes or weakens, its share in the overall strength is minimal, and you won't even notice it in how the entire cable behaves. Plus, it's way easier to create a flexible shape from tens of thousands of thin elements. The cable can smoothly wrap around the towers, forming a huge parabola over the span, whereas a rod of that diameter simply won't bend without plastic deformation. The process of creating main suspension cables is also nothing like how regular steel cables are made at the factory. Nobody sends a finished cable to a construction site that's 3 feet thick and thousands of feet long. That kind of monster would be impossible to deliver or hoist into position. So the main cables of suspension bridges are spun on site. It starts with installing temporary pilot cables between the towers. A traveling carriage runs along them, shuttling back and forth across the entire span. A reel of steel wire is mounted on the carriage. Each trip of the carriage pulls another wire between the shores. One end of the wire is anchored on one side. The carriage holds the reel across the span. The wire is secured on the other shore, and the excess is cut off. Then the next wire, and this happens tens of thousands of times. To keep this insane marathon from turning into chaos, the wires are organized into so-called strands, or sub-cables. For example, several hundred parallel wires are bundled together into one strand of a specific diameter. First, all the wires get pulled tight with a bit of slack. Then, special jacks even out the tension, so each individual wire carries roughly the same load. Next, the bundle gets clamped with rings, or special clamps to keep it from splaying apart. Once you've got enough of these bundles, they're brought together and clamped again into one massive structural cylinder. A spiral wrapping of thin round wire goes on top to hold the shape, plus a protective layer of paint or other anti-corrosion coating. At this stage, the cable can already hold an incredible amount of force. Picture this. Hanging from it is a bridge span, a steel truss or box girder that supports the roadway. This span transfers its load through suspender cables onto the main cables. Every vehicle crossing the bridge adds several tons to the system, sometimes dozens if we're talking about a semi or a convoy of trucks. Wind pushes against the structure's lateral surface with forces that can reach thousands of kilonewtons during a storm. Ultimately, the main cables feel all of this, stretching literally a few inches along their entire length while staying within elastic deformation limits. The beauty of a suspension bridge is that the cable works purely in tension, not bending or compression. That's the ideal mode for high-strength steel. The elastic modulus and tensile strength of these wires are engineered so working stresses stay well below the breaking point, even accounting for wind gusts, temperature swings, and traffic surges. During the design phase, engineers model every possible loading scenario. Both lanes completely packed with semi-trucks, sudden braking, seismic effects. The result is an acceptable range of cable stretch and sag within which the bridge remains safe and comfortable for users. Interestingly, despite the system's rigidity, the main cables aren't absolutely stationary. They breathe along with the bridge. When heated on a sunny day, the steel expands and the cable sags slightly. During nighttime cooling, tension increases and sag decreases. In windy weather, you can notice a gentle swaying of the deck. In reality, the cables themselves are also moving, though it's invisible to the eye. It's precisely this living, flexible behavior that allows suspension bridges to handle dynamic loads better than rigid, overly stone-like structures. Excessive rigidity is exactly what led to disasters throughout the history of bridge building, while controlled flexibility allows the dissipation of vibrational energy. A separate critical topic is protecting cables from corrosion. Steel fears moisture and salt spray, especially in coastal regions like San Francisco. If water and